Hello there, and welcome to Physics with William, where we take some of the stranger ideas in science, give them a little room to breathe, and see whether the universe becomes any less confusing when nobody's rushing us through it. Tonight we're going to meet a particle that sounds as though it belongs in science fiction, but is very much part of ordinary physics. It is called the Antiproton, and despite the dramatic name, it is not an evil proton, a damaged proton, or a proton that has somehow decided to rebel against the rest of matter. It is the antimatter partner of the proton, matching it in some properties with remarkable precision, while reversing others in exactly the way modern particle physics predicts. That simple statement leads us into one of the deepest puzzles in science, because if nature is perfectly capable of making both protons and antiprotons, we have to wonder why almost everything we see around us appears to be made from only one of them. Before we get into that, I would love to know where you're listening from tonight. Perhaps you're already in bed with the lights low, perhaps you're sitting somewhere with a cup of tea that you intended to drink 10 minutes ago and have only just remembered, or perhaps this is playing quietly while you're doing something else and pretending that you're definitely still paying attention. Wherever you happen to be, let me know where in the world you're listening from, and what time it is for you right now. If you find these calm journeys through physics interesting or useful for winding down, you can also leave a like and subscribe to the channel. It helps this little corner of science reach more people who enjoy learning about the universe without being shouted at by enthusiastic diagrams. For now, get comfortable, let everything else become slightly less urgent, and we will begin with the particle the antiproton is paired with, because understanding the antiproton starts with understanding what a proton actually is. The proton is one of those objects most of us encounter very early in science lessons. We are usually introduced to the atom as having a small central nucleus containing protons and neutrons, with electrons associated with the region around it. The proton carries positive electric charge, while the electron carries negative electric charge. That basic picture is simplified, but it is useful, and it tells us something important. Protons are not rare or exotic. They are among the most common pieces of matter in the universe. Every ordinary hydrogen nucleus is a proton. The heavier elements contain many protons packed together with neutrons inside their nuclei. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the silicon in rocks, and the iron in the earth all contain protons. If you remove protons from ordinary matter, there would not be much ordinary matter left to complain about. For a long time, the proton was treated as though it were a basic particle with no internal parts. We now know that this is not the case. The proton is made from smaller objects called quarks, held together by the strong interaction. Its internal structure is far more active than the tidy schoolbook image of a small solid sphere might suggest. Inside a proton, quarks and the particles associated with the strong interaction are involved in constant quantum activity. The proton is therefore not a tiny billiard ball sitting peacefully inside the nucleus. It is a complicated quantum system that happens to behave as a stable particle when we observe it from the outside. Nature has managed to hide a surprising amount of activity inside something extremely small, which is perhaps unfair to anyone who was hoping the atom would be the simple part of physics. Now imagine taking the essential particle properties that distinguish a proton as matter and replacing them with their antimatter counterparts. The result is an antiproton. An antiproton has the same mass as a proton, as far as our measurements can determine, but its electric charge is negative rather than positive. That alone makes it sound like a simple reversal, but the difference goes deeper. Because the proton contains quarks, the antiproton contains the corresponding antiquarks. Its internal structure is built from antimatter constituents. It is not merely a proton whose electric charge has been switched. The particle itself belongs to the antimatter side of the relationship. This is where the word antimatter can cause a little trouble, because it invites all sorts of imaginative interpretations. Antimatter is sometimes treated in popular stories as though it were a mysterious substance with completely reversed physical behaviour. You might imagine that an antiproton has negative mass, falls upward, travels backward through time, or quietly resents nearby furniture. None of those descriptions is what physicists mean when they call it antimatter. The antiproton has ordinary positive mass. It carries energy. It responds to forces. It can move through space just as any other particle can. It does not automatically race toward matter, and it does not behave like a whole in reality. What makes it an antiparticle is a specific reversal of certain quantum properties, while other properties remain the same. The easiest comparison is with the electron and the positron. An electron has negative electric charge. Its antiparticle, the positron, has the same mass but positive electric charge. The antiproton follows a similar pattern relative to the proton. The proton has positive charge, while the antiproton has negative charge. But there is one immediate source of confusion. If both an electron and an antiproton are negatively charged, why are they not the same particle? The answer is that charge alone does not define a particle. The electron is much lighter and belongs to a completely different class of particles. It has no known internal quark structure. The antiproton is heavy compared with the electron and is built from antiquarks. Two objects can carry the same electric charge and still be completely different, just as two people can wear the same color coat without becoming the same person. The relationship between the proton and antiproton is especially interesting because it is so precise. If we compare their masses, they appear equal to extraordinary accuracy. If we compare the size of their electric charges, those match as well, with the direction of the charge reversed. Their magnetic properties also show the corresponding antimatter relationship. Experiments have spent years testing these similarities, because even a tiny difference could be important. Modern physics predicts a deep connection between matter and antimatter, and the proton and antiproton provide one of the clearest places to test whether that connection really holds. Suppose you had two extremely carefully made clocks that were expected, according to the design, to behave as perfect counterparts. You would not learn much by glancing at them once and deciding they seemed close enough. You would compare them again and again. You would measure how they behave under different conditions. You would look for tiny disagreements that might reveal something hidden in the mechanism. Physicists do something similar with protons and antiprotons. The more accurately the two can be compared, the more strongly we can test the underlying rules of particle physics. If the antiproton were even slightly heavier than expected, or if the magnitude of its charge differed from that of the proton, it would force scientists to rethink some very basic assumptions. So far, the antiproton has been remarkably cooperative. It continues to behave very much as our best established theories say it should. That may sound less exciting than discovering a dramatic failure, but precision agreement is extremely valuable. Every successful test tells us that if new physics is hiding somewhere, it must either appear under conditions we have not yet reached or produce differences smaller than our current measurements can reveal. Science often advances by finding surprises, but it also advances by discovering just how difficult those surprises are to find. There is another reason the antiproton feels unusual. Protons are everywhere in ordinary life, while antiprotons are not. You can spend your whole day surrounded by ordinary matter without knowingly encountering a single antiproton. The reason is not that antiprotons cannot exist. They certainly can. The problem is that our surroundings are a very unfriendly place for them. Almost every solid object around you contains enormous numbers of protons and neutrons. An antiproton that enters ordinary material has a good chance of interacting with one of those particles, and when matter and antimatter meet under the right conditions, annihilation can occur. The word annihilation sounds as though the particles simply vanish into nothing, but that is not what happens. Energy and other particles are produced. The original proton and antiproton cease to exist as a proton and antiproton, but their energy does not disappear. The interaction transforms what was present into new forms. This is another place where science fiction sometimes gives the process a slightly misleading reputation. Matter and antimatter do not cancel reality itself. They interact according to ordinary conservation laws, although the amount of energy involved can be impressive because the mass of the original particles contributes to what becomes available in the final products. If an antiproton could somehow be placed in completely empty space and kept away from ordinary matter, it would not immediately vanish just because it was antimatter. It could continue to exist. The difficulty is maintaining that isolation. A normal container is made from matter, which means placing an antiproton inside an ordinary box and allowing it to touch the wall would rather defeat the purpose of the box. Scientists therefore use carefully arranged electric and magnetic fields to control antiprotons without letting them rest against physical surfaces. Because antiprotons carry electric charge, those fields can guide them, slow them, and in specially designed traps keep them confined in regions of extremely good vacuum. There is something wonderfully awkward about producing antimatter in a laboratory. First, scientists build enormous machines to accelerate particles to very high energies so antiprotons can be created in collisions. Then, after finally producing the antiprotons, they spend a great deal of effort slowing them down again. High energy is useful for creation, but low energy is often much better for careful measurement. It is rather like spending an afternoon launching a very expensive object across the room and then devoting the evening to finding a polite way of asking it to stop. The antiproton is also not something that exists only because humans learned how to make particle accelerators. Nature produces antiprotons too. High-energy cosmic rays travelling through space can collide with matter and create antiprotons among the resulting particles. Powerful astrophysical environments can generate antimatter through energetic processes. Instruments studying cosmic rays have detected antiprotons arriving naturally. So the antiproton is not artificial in the sense of being a human invention. Particle accelerators simply give us a controlled way to reproduce conditions energetic enough for nature to make them where we can study them. This immediately leads to a larger question. If nature can produce antiprotons, why do we not see antimatter everywhere? Why is the Earth not surrounded by equal quantities of protons and antiprotons? Why do stars appear to be made mainly from ordinary matter? Why is your left hand not matter while your right hand is antimatter, which would at least make handshakes considerably more memorable? The answer is that the observable universe seems to contain much more ordinary matter than antimatter, and we do not yet have a complete explanation for why this is so. That puzzle reaches back to the early universe. When the universe was extremely hot and energetic, conditions were suitable for the creation of many kinds of particles and antiparticles. Our understanding suggests that matter and antimatter should have been produced in closely related amounts. As the universe expanded and cooled, matter and antimatter particles encountered each other and annihilated. If they had existed in exactly equal numbers and behaved in a perfectly balanced way, we might expect almost all of them to have disappeared into radiation, leaving behind a universe with very little matter available to form stars, planets, or people lying awake listening to physics. Yet some matter survived. In fact, enough survived to build everything we can see. The simplest way to think about the situation is that the early universe appears to have ended up with a very small excess of matter over antimatter. After most matter and antimatter annihilated, that tiny leftover amount of matter remained. Over enormous stretches of time it became gas, stars, galaxies, planets, chemistry, biology, and eventually beings capable of wondering why there was any matter left in the first place. The antiproton therefore represents much more than a strange mirror image of a familiar particle. It is connected to the question of why anything made from matter exists at all. If scientists can discover some tiny difference between the behavior of matter and antimatter, that difference might help explain how the early universe developed its imbalance. We already know of certain processes in particle physics that distinguish matter from antimatter in subtle ways, but the full explanation for the cosmic dominance of matter remains incomplete. The antiproton is one of the objects we can use to investigate whether additional differences are waiting to be found. There is another useful way to understand how complete the antimatter mirror can become. If you take an ordinary proton and associate it with an ordinary electron, you have the basic ingredients of hydrogen. If instead you take an antiproton and associate it with a positron, the antimatter partner of the electron, you can make antihydrogen. Antihydrogen is not imaginary. Scientists have produced it and learned how to hold it for experimental study. It behaves like an atom, because that is exactly what it is, except its components are antiparticles. This gives physicists an extraordinary comparison. Hydrogen is one of the best studied atomic systems in all of science. Its behavior has been measured with tremendous precision. Antihydrogen gives us a mirrored version to test against it. Scientists can ask whether antihydrogen interacts with light exactly as expected, whether its internal energy structure matches that of hydrogen, and whether gravity affects it in the way our theories predict. These experiments are difficult, partly because making and trapping enough antihydrogen is not exactly something one can accomplish with a spare afternoon and a reasonably tidy garage, but the measurements are becoming increasingly precise. All of this helps strip away one of the most persistent misconceptions about antimatter. The antiproton is not mysterious because scientists have no idea how it behaves. In many respects, they understand its behavior extremely well. It is mysterious because its existence exposes a mismatch between the apparent symmetry of the laws and the obvious imbalance of the universe. When we study an antiproton closely, it looks like precisely the antimatter counterpart we expected. When we look at the cosmos, however, we do not see matter and antimatter represented in anything like equal abundance. Imagine discovering that a factory produces shoes according to a perfectly balanced design. One left shoe for every right shoe. You inspect the machinery and find no obvious bias. You check the production rules and everything says the numbers should match. Then you visit the warehouse and discover almost nothing but left shoes. At that point, the interesting question is no longer whether right shoes can exist. You have already seen them. The question is what happened between production and the warehouse. Particle physics faces something vaguely similar, although fortunately the fate of the universe does not depend on footwear. For the antiproton itself, though, the most important fact at this stage is that it is real, measurable, and deeply connected to the proton without being identical to it. It has the proton's mass, the opposite electric charge, and an internal structure built from antiquarks rather than quarks. It can be created when enough energy is available. It can survive if prevented from touching ordinary matter. It can be trapped, slowed, measured, and even combined with a positron to build an antimatter atom. Nothing about it requires a separate set of magical rules. The same physics that describes ordinary particles also describes their antimatter partners. That may be the strangest part of all. The antiproton does not sit outside our understanding of nature. It sits right in the middle of it. The theories that describe ordinary matter naturally make room for antimatter. Once physicists learned to look in the right way and reached high enough energies, the missing partners began to appear. The electron had the positron. The proton had the antiproton. Neutrons and quarks also had their own corresponding antiparticles. What initially looked like a peculiar mathematical possibility turned out to be a basic feature of the particle world. To see how physicists reached that conclusion, we need to move back to a time before anyone had detected an antiproton, before antimatter had become a familiar word in science, and before researchers knew whether the strange counterparts appearing in their equations belonged to the real universe. The trail begins not with a particle accelerator producing antiprotons, but with an attempt to understand the electron, a theoretical problem that unexpectedly suggested nature had been keeping an entire, mirrored set of particles just out of sight. The trail begins before anyone had seen an antiproton, at a time when even the idea of antimatter would have sounded unnecessary. Matter already seemed complicated enough. Physicists had atoms, electrons, radiation, electric fields, magnetic fields, and a growing collection of experimental results that refused to fit comfortably into the older picture of nature. By the beginning of the 20th century, the atom was no longer thought to be indivisible. Light was behaving in ways that forced scientists to rethink what a particle and a wave really meant. and Einstein had shown that measurements of space and time depended on motion. Physics was becoming extraordinarily successful and slightly unsettling at the same time. Just when one problem appeared to be under control, another would quietly arrive and ask everyone to rearrange the furniture. The electron had been discovered near the end of the 19th century, and it presented physicists with a remarkably small object carrying negative electric charge. Once the structure of atoms began to emerge, electrons became essential to explaining electricity, chemistry, and the way atoms interacted with one another. For a while, it was tempting to imagine that understanding the electron would simply require better measurements. Instead, the electron became one of the places where the new quantum world revealed itself most clearly. It could behave in ways that classical physics did not predict, and describing it properly required a theory that was still being invented. Quantum mechanics developed during the 1920s as physicists tried to explain the behavior of atoms and radiation. It was successful almost immediately, but it came with a problem. The early mathematical descriptions of quantum particles worked best when those particles were moving much more slowly than light. Einstein's special relativity, however, had already shown that the rules governing fast-moving objects were different from those of ordinary everyday motion. A complete description of the electron had to respect both frameworks. The electron was a quantum object, but it was also capable of moving at speeds where relativity mattered. Nature was not going to accept two separate sets of instructions simply because the mathematics was inconvenient. This was the problem that Paul Dirac began working on. Dirac was a young British physicist with a reputation for unusual quietness and exceptional mathematical ability. He wanted an equation that could describe the electron using quantum mechanics while remaining consistent with special relativity. That goal sounds straightforward when stated in one sentence, but it was anything but straightforward in practice. The existing approaches did not combine the two theories in the way physicists wanted. Dirac searched for a mathematical structure that would work, and in 1928 he found one. The new theory described important properties of the electron with impressive success. It naturally accounted for characteristics that had previously looked as though they needed to be added separately, including the electron's intrinsic angular momentum. That alone made the work important. But the mathematics contained an unexpected feature. The equation did not produce only the familiar electron states physicists wanted. It also allowed another set of possibilities that were difficult to interpret. In simplified terms, the theory appeared to contain states associated with energies below what physicists expected for an ordinary electron. The details were technical, but the difficulty was obvious enough. If those states were physically available in the wrong way, why would an ordinary electron not simply keep dropping into lower and lower energy states without end? Something about the interpretation had to change. Dirac initially tried to make sense of this by imagining that the apparently troublesome states might already be occupied. A missing particle in that filled background could then behave like something carrying positive electric charge. The proposal went through several stages as he worked out what the mathematics was trying to say. At one point he considered connecting the unfamiliar state with the proton, which was positively charged and already known. That possibility did not survive because the proton was far heavier than the electron. The theory was pointing towards something much more specific. There ought to be a particle with the same mass as the electron but with the opposite electric charge. That was a very strange thing to predict in the early 1930s. No one had a drawer labelled positively charged electrons. Ordinary atoms contained negatively charged electrons, while positive charge was associated with atomic nuclei. The known world did not seem to require an electron twin. Yet the theory kept insisting that such a possibility belonged to the same mathematical framework as the electron itself. It is difficult to recreate just how radical that idea was because antiparticles are now part of the standard language of physics. We learn the word antimatter and quickly become accustomed to it. But imagine being told at the time that every familiar particle might belong to a larger pattern in which nature provided a corresponding partner with certain properties reversed. There was no guarantee that this was how the universe actually worked. mathematics can suggest possibilities that experiments later reject. Physicists therefore needed evidence. That evidence came from above rather than from a particle accelerator. Earth is constantly being struck by cosmic rays, energetic particles arriving from space. When these particles collide with atoms in the atmosphere, they can produce showers of secondary particles. Long before modern accelerators could create every type of collision scientists wanted, cosmic rays provided nature's own high-energy laboratory. The difficulty was that nature did not schedule its experiments conveniently. Researchers had to build detectors, wait for the right events, and interpret the tracks left behind. Carl Anderson, an American physicist working at the California Institute of Technology, was studying cosmic rays using a cloud chamber. A cloud chamber contains vapor arranged so that a charged particle passing through can leave a visible trail. If a magnetic field is present, the path of the charged particle curves. The direction of that curvature depends on the sign of the electric charge, while the amount of curvature and other observations help scientists work out information about the particle's momentum. In 1932, Anderson photographed a track that presented an intriguing combination of properties. The particle curved as though it carried positive charge, but its behavior suggested that it had approximately the mass of an electron, rather than the far greater mass of a proton. Here was the sort of object Dirac's theory had implied. It was a positively charged counterpart of the electron. The particle became known as the positron. For the first time, an antiparticle had been observed experimentally. The discovery did more than add one more item to the growing particle catalogue. It changed the status of the whole idea. Antimatter was no longer a mathematical curiosity that might disappear after a better interpretation came along. Nature had produced a particle that matched the predicted pattern. The electron had an antimatter partner. The positron was not an electron that had somehow changed its charge. It was a distinct particle. It had the same mass as the electron and the opposite electric charge. If a positron moved through a magnetic field, it curved differently from an electron because its charge had the opposite sign. In other respects, the relationship between the two was remarkably close. One could now begin to think of the electron not as an isolated object, but as one member of a pair. Further experiments soon strengthened the case. Positrons were observed in cosmic ray events, and researchers saw processes in which energetic radiation produced an electron and a positron together. This was especially important because it revealed something fundamental about how matter and antimatter could appear. Energy could be transformed into a particle, and its antiparticle under the right conditions. The process did not create matter from absolute nothingness. The incoming energy and the surrounding system provided everything required, and the physical conservation rules remained intact. What changed was the form in which the energy existed. The reverse process was also observed. When an electron and a positron encountered each other, they could annihilate, producing radiation. Again, annihilation did not mean that something had been erased from the universe. The particles ceased to exist as an electron and a positron, while their energy appeared in another form. The term sounds dramatic because it suggests complete destruction, but physics is much more careful than that. Nature changes the bookkeeping entries without throwing away the ledger. These paired processes gave antimatter a much clearer physical meaning. A particle and its antiparticle could be created together when enough energy was available, and they could transform into other forms when they met. The symmetry was not merely an abstract resemblance between two particles. It was built into real interactions that could be observed. Once the positron was accepted, an obvious question followed. Was the electron special, or did the same pattern apply more generally? By then, physicists knew about the proton. It was positively charged and enormously heavier than the electron. If the new antimatter idea was truly fundamental, then the proton should have a corresponding antiparticle too. This hypothetical particle would have the proton's mass but negative electric charge. It would be the antiproton. Predicting the antiproton was easier than finding it. the positron had appeared naturally in cosmic ray observations, because producing an electron and positron pair requires much less energy than producing a proton and antiproton pair. Protons are far more massive than electrons. Creating a new antiproton therefore demands a collision with enough available energy to produce that considerable mass while satisfying all the conservation requirements of the interaction. By the 1950s, accelerator technology had advanced far enough to make a deliberate search possible. Instead of waiting for cosmic rays to provide suitable events, physicists could accelerate particles themselves, direct them into a target, and examine what came out. The challenge was to reach energies high enough to create antiprotons in useful numbers. At the University of California in Berkeley, a machine called the Bevatron was built to accelerate protons to the required range of energies. Its size and complexity reflected the enormous difference between producing an antiproton and performing an ordinary laboratory experiment. The accelerator pushed protons to very high speeds and sent them into a target. Each collision could produce a complicated collection of new particles. Somewhere among those products, the researchers hoped, there would occasionally be a negatively charged particle with the mass of a proton. The difficulty was identification. Negative charge alone was nowhere near enough. Electrons were negatively charged. Other negatively charged particles could also be produced. The researchers needed to determine whether a candidate moved and interacted in the way expected for a particle as heavy as a proton. In 1955, Emilio Segre, Owen Chamberlain, Clyde Wiegand, and Thomas Ypsilantis carried out the experiment that provided the decisive evidence. Their apparatus selected negatively charged particles produced in high-energy proton collisions and passed them through a sequence of detectors. By comparing their momentum with measurements related to their speed, the team could distinguish a heavy antiproton from lighter particles travelling through the equipment. The signal was difficult because antiprotons were rare among the much larger number of ordinary particles produced. The experiment therefore depended on carefully designed filtering rather than simply watching a collision and hoping something unusual waved from the crowd. The researchers had to rule out alternative explanations and show that the particles they were detecting had the characteristics expected of the proton's antimatter counterpart. They succeeded. The antiproton existed. Roughly 2 decades after the positron had revealed the first confirmed antiparticle, the proton had acquired its own experimental mirror. Antimatter was no longer an idea attached mainly to electrons. It was becoming a general feature of particle physics. There was an important difference between the antiproton and the positron that scientists would only understand fully later. The electron appears to be elementary, meaning that no smaller internal constituents have been found inside it. The proton is not elementary. It has an internal structure. At the time of the antiproton's discovery, the modern quark model had not yet been developed, so researchers did not describe the antiproton in the language we use today. Later discoveries would show that a proton contains quarks, while an antiproton contains the corresponding antiquarks. This meant that antimatter symmetry operated not only at the level of whole particles, but within their internal building blocks. The antiproton was not a solid proton with its charge turned around. Its constituent structure itself was the antimatter counterpart of the proton structure. Soon after the antiproton was discovered, physicists also established the existence of the antineutron. A neutron carries no overall electric charge, which makes the idea of an antineutron useful for clearing up a common misunderstanding. If antimatter meant nothing more than reversing electric charge, a neutral particle would have no obvious antimatter partner. Yet the neutron does have one. The distinction lies in the deeper quantum properties and, as later understood, in the replacement of quarks by antiquarks. The discovery of these antiparticles gradually changed the way scientists pictured the particle world. Instead of a collection containing electrons, protons, neutrons, and a growing number of other particles, there was a corresponding antimatter structure running alongside much of the same catalogue. Whenever a new particle was identified, physicists could ask about its antiparticle. Sometimes the answer was a separate particle. In certain cases, a particle could be identical to its own antiparticle. Nature apparently had decided that one simple rule would have been too relaxing. The terminology also became more precise. Antimatter was not a new force or a separate kind of energy. It was matter built from antiparticles. A positron was antimatter because it was the electron's antiparticle. An antiproton was antimatter because it was the proton's antiparticle. Combine an antiproton with a positron under suitable conditions and you can produce antihydrogen, the antimatter counterpart of a hydrogen atom. In principle, more complicated antiatoms can also exist. This leads to one of the more amusing consequences of the idea. An object made entirely of antimatter would not necessarily look unusual from a distance. Imagine an antihydrogen atom completely isolated from ordinary matter. It could have an antiproton at its centre and a positron associated with it. The system would not glow with a special antimatter colour or announce itself with ominous music. Its internal electromagnetic behaviour would closely mirror that of ordinary hydrogen. Extend the idea far enough, and one can imagine antimatter gas, antimatter stars, or even larger objects built from antiparticles. Whether such large antimatter regions actually exist in the observable universe is a different question, and there are strong observational reasons for thinking ordinary matter dominates our surroundings. But the basic laws of physics do not say that antimatter must remain as lonely particles drifting through a laboratory. Antiparticles can form structures just as particles can, provided they are not constantly being introduced to ordinary matter. This created a puzzle that became more serious as cosmology improved. If nature provides matter and antimatter partners so consistently, why is the universe around us overwhelmingly made from matter? The early universe was extraordinarily hot. The energies involved were far beyond anything encountered in ordinary modern environments. Under those conditions, particle and antiparticle creation would have been common. Matter and antimatter should have been produced in enormous quantities. As the universe expanded, it cooled. Particles and antiparticles encountered one another and annihilated. If matter and antimatter had existed in perfectly equal amounts and no process favoured either side, almost all of them could have disappeared in paired annihilations, leaving mostly radiation behind. Something prevented that simple ending. There was a slight surplus of matter. After most of the matter and antimatter had destroyed each other as particle pairs, the excess matter remained. That residue became the material from which later structures formed. Stars eventually ignited, galaxies assembled, planets appeared, chemistry grew complicated. Much later, a species arose that became sufficiently comfortable to name itself, build particle accelerators, and investigate why it had been allowed to exist. The imbalance required was small compared with the enormous quantities of matter and antimatter thought to have been present early on. Yet that small difference made all the difference. Without surviving matter, there would be no atomic nuclei, no ordinary atoms, and no familiar material universe. This is why antimatter research became connected with a question much larger than the particles themselves. Finding the positron and antiproton confirmed that the antimatter partners existed. It did not explain why they were so scarce around us today. Scientists discovered that certain interactions do treat matter and antimatter slightly differently. Those differences are real and important, but the amount of asymmetry found in known processes has not, by itself, provided a complete explanation for the observed dominance of matter in the universe. There may be additional effects we have not yet measured, particles we have not discovered, or conditions in the early universe that we do not fully understand. That possibility makes precision antimatter experiments especially valuable. If a proton and antiproton were found to differ in some forbidden way, the result could reveal a crack in the current framework. If antihydrogen behaved differently from hydrogen beyond what established physics allows, that would demand explanation. Even confirming that no such discrepancy exists teaches us something, because it rules out possible solutions to the larger mystery. There is a nice contrast between the historical birth of antimatter and the reputation antimatter later acquired. In popular culture, it often appears as a spectacular fuel, weapon, or source of almost unreasonable amounts of energy. In actual physics, the story began with a mathematical consistency problem involving the electron. There was no explosion, no secret antimatter vault, and no scientist announcing that humanity had discovered a substance from a mirror universe. There was an equation that behaved strangely, followed by a particle track and a detector, followed years later by increasingly powerful accelerator experiments. That sequence is worth remembering because it shows how science often advances. A theory can reveal a possibility no one was specifically looking for. An experiment can then test whether the possibility corresponds to nature. If the object appears, the theory becomes more credible, but also creates new questions. The positron confirmed part of Dirac's insight, but immediately encouraged physicists to ask about other antiparticles. The antiproton confirmed the broader pattern, but then made the cosmic matter imbalance even harder to ignore. By the middle of the 20th century, antimatter had moved from theoretical surprise to established physical reality. The electron had a positron, the proton had an antiproton, the neutron had an antineutron. Later, the quark model would reveal antimatter partners at an even more fundamental level, with antiquarks corresponding to quarks and combining to form particles such as the antiproton. Once that internal picture became clear, the antiproton stopped looking like a simple proton carrying the wrong electrical sign. It became something more interesting. The proton itself is an active, complicated object whose mass is not merely the sum of a few tiny components sitting quietly inside it. The strong interaction, the motion of quarks, and the behaviour of the fields binding them all contribute to what the proton is. The antiproton reproduces that complexity using antimatter constituents. That is where the next part of the story naturally takes us, because saying that the antiproton has the same mass as the proton and the opposite charge is accurate, but it barely begins to describe what is happening inside. To understand why these two particles resemble one another so closely, we need to look beneath their outer labels and see how quarks, antiquarks, charge, mass, and the strong interaction build two remarkably matched versions of the same underlying structure. To understand why the antiproton is such a convincing partner to the proton, it helps to stop thinking of either particle as a tiny solid ball with a charge painted on the outside. That old picture is useful when we're first learning about atoms, because it lets us imagine a nucleus as a compact collection of protons and neutrons surrounded by electrons. But once we look closely enough, the proton itself turns out to contain an active internal world. The antiproton contains a corresponding world of its own, built according to the same physical rules, but with the relevant matter properties reversed. This is where the phrase antimatter twin becomes much more precise, because the resemblance between the proton and antiproton is not simply a coincidence in their weight and electric charge. Their internal structures are related at a much deeper level. A proton belongs to a family of particles called hadrons. Hadrons are particles made from quarks and held together by the strong interaction. The proton contains three main quarks that determine its basic identity. Two of these are called up quarks and one is called a down quark. Those names are simply labels. There is nothing physically higher about an up quark or lower about a down quark, and neither spends its day travelling in the direction suggested by its name. Particle physicists needed words to distinguish different kinds of quarks, and at some point the vocabulary became rather creative. The antiproton has the corresponding antimatter arrangement. Instead of two up quarks and one down quark, it contains two anti-up quarks and one anti-down quark. Antiquarks have the same masses as their corresponding quarks, while several of their quantum properties are reversed. When those antiquarks combine in the correct way, the result is an antiproton with precisely the overall properties expected for the proton's antiparticle. This immediately explains one of the most obvious differences between the two particles. The proton carries positive electric charge, while the antiproton carries negative electric charge. The total charge comes from the charges of the quarks or antiquarks inside. Individual quarks carry fractional amounts of electric charge, although isolated quarks are not normally found wandering around by themselves. When the three main quarks inside a proton are considered together, their charges combine to produce the familiar positive charge of the proton. Replace those quarks with the corresponding antiquarks, and every relevant charge is reversed. The resulting total is the same size but negative. This is why an antiproton is not simply a proton that has somehow picked up an extra electron. If an ordinary proton attracts an electron, the combination becomes a hydrogen atom, not an antiproton. The proton inside that atom remains an ordinary proton. Its quark structure has not changed. The negative electron simply balances its positive electric charge from the outside. An antiproton is fundamentally different because the constituents inside it are antiquarks. Its negative charge is part of what the particle itself is. The same distinction helps us avoid another common misunderstanding. An antiproton and an electron both carry negative electric charge, but that does not make them closely related. An antiproton is almost 2,000 times more massive than an electron, and has a complex internal structure governed by the strong interaction. An electron, as far as experiments can tell, has no smaller internal constituents. If you could somehow place the two beside each other and ignore the inconvenience of trying to inspect objects this small, their shared negative charge would be one of the few obvious similarities. It would be rather like deciding that a cargo ship and a teaspoon are basically the same object, because both happen to be made of metal. The mass of the antiproton is especially interesting because it matches the mass of the proton extremely closely. At first glance, we might imagine that the mass of a proton simply comes from adding together the masses of the three quarks inside it. That would be a pleasantly straightforward explanation. Unfortunately for anyone hoping for a quiet evening, most of the proton's mass does not arise that way. The quarks themselves contribute only a relatively small part of the total. Much of the proton's mass comes from the energy associated with the strong interaction, including the motion of quarks and the activity of the fields binding the system together. In modern particle physics, mass and energy are deeply connected, so the energetic internal behavior of the proton contributes substantially to the mass we measure from outside. Inside the proton, the picture is not simply three quarks sitting motionless at fixed positions. The strong interaction is carried by particles called gluons, and the internal environment contains a constantly changing mixture of quarks, antiquarks, and gluons. The three main quarks establish the proton's identity, but around them is a much richer quantum system. Quark and antiquark pairs can appear briefly within the internal activity. Gluons interact with one another, and momentum is shared among the various components. The proton is less like a neatly packed box containing three marbles, and more like a very small, highly organized storm that somehow maintains a stable overall identity. The antiproton mirrors this complexity. Its main constituents are three antiquarks, but it also contains the corresponding activity of gluons and temporary quark and antiquark contributions. The strong interaction works inside the antiproton just as effectively as it works inside the proton. The result is that the enormous contribution made by strong interaction energy to the proton's mass is matched in the antiproton. This is one reason the equality of their masses is so significant. Nature is not merely matching three simple objects, it is matching the behavior of two complicated quantum systems. Gluons deserve a moment of attention because they are responsible for holding quarks together. The strong interaction is extraordinarily powerful at the distances inside particles such as protons and antiprotons. Unlike electric forces, which become weaker as charged objects are separated, the strong interaction between quarks behaves in a way that makes pulling an individual quark completely free extremely difficult. As more energy is added in an attempt to separate quarks, the system eventually tends to use that energy to create new particles rather than provide one isolated quark. This property is known as confinement. It is the reason physicists do not normally observe individual quarks travelling freely through detectors. Quarks appear bound inside composite particles. The same is true for antiquarks. The antiquarks inside an antiproton are confined together by the strong interaction, giving the antiproton the same sort of stable composite structure as the proton. The strong force does not suddenly become an anti-force inside antimatter. There is no separate set of interactions reserved for antiparticles. The same underlying strong interaction that binds quarks inside a proton binds antiquarks inside an antiproton according to the rules of quantum theory. This is one of the recurring lessons of antimatter. It is not another universe of physics with all the instructions reversed. Matter and antimatter belong to the same framework. Electric charge is simply the most familiar property that changes between the proton and antiproton. Other quantities associated with the particle are reversed as well. One of these is called baryon number. The proton belongs to the category of particles known as baryons, and an antiproton carries the corresponding opposite baryon identity. This distinction becomes important when we describe particle reactions, because physical processes must obey particular conservation rules, at least within the interactions we have observed under ordinary conditions. There is no need to turn baryon number into a piece of mathematics to appreciate what it does. Think of it as one of the labels nature uses for keeping track of certain kinds of matter. A proton carries the matter version of that label. An antiproton carries the opposite version. When particles interact, the before and after states must fit the allowed bookkeeping. This is why producing an antiproton in a collision usually requires the creation of other particles as part of the same event. Nature does not simply reverse one proton and hope nobody checks the paperwork. The magnetic behaviour of the proton and antiproton gives scientists another powerful comparison. Because the proton contains moving electrically charged constituents and possesses an intrinsic quantum property known as spin, it behaves somewhat like a tiny magnet. The antiproton has the corresponding antimatter magnetic behaviour. Its magnetic moment points according to the reversed relationship expected for an antiparticle. Measuring this accurately is difficult because the particles are extremely small and antiprotons are not available by the bucket. Researchers must create them, slow them, isolate them from ordinary matter, and trap them using electromagnetic fields. Once an antiproton has been confined, its behaviour in carefully controlled magnetic environments can reveal its properties with remarkable precision. The reason scientists care about these measurements is not simply that they want a more detailed entry for the antiproton in a reference book. Particle physics predicts a profound symmetry between particles and antiparticles. The proton and antiproton should have exactly the same mass. Their electric charges should have equal magnitude and opposite signs. Their magnetic properties should show the corresponding reversal. If researchers found a genuine difference outside those expected reversals, the result would indicate that something fundamental in our present description of physics was incomplete. Imagine manufacturing two keys designed as perfect counterparts according to an exact set of rules. You measure every ridge, every angle, every length, and every tiny surface feature. If the design requires a precise relationship, and one key is found to be slightly different, in a way the instructions forbid, you have learnt something about the manufacturing process. With protons and antiprotons, the stakes are considerably higher, because the manufacturer is nature, and the instructions are some of the deepest principles in particle physics. So far, repeated experiments have found an extraordinary level of agreement. The mass relationship between proton and antiproton has been tested with very high precision. Their charge relationship has also been examined. Measurements of their magnetic properties continue to agree impressively with the expected matter and antimatter symmetry. That agreement makes the disappearance of antimatter from the observable universe even more intriguing. If antiprotons behaved obviously differently from protons, one could imagine those differences accumulating in the early universe and favouring one over the other. But when we place the particles under careful laboratory examination, they seem almost determined not to provide such an easy explanation. There are known processes involving other particles where matter and antimatter do behave differently in subtle ways. These differences are extremely important in modern physics, particularly when scientists try to understand why matter survived after the early universe cooled. Yet the proton and antiproton remain astonishingly well matched in the fundamental properties that researchers can compare directly. It is useful here to think more carefully about what the word same means. Saying that a proton and an antiproton have the same mass does not mean they are the same particle. A kilogram of feathers and a kilogram of books can have the same mass without being identical objects, although one of them is considerably more annoying to clean up if dropped from a balcony. In particle physics, mass is one property among several. Two particles can share a mass while differing in charge and other quantum labels. Likewise, saying that their charges are opposite does not mean everything else about them must be opposite. The antiproton does not have negative mass. If it is accelerated, it responds normally to the applied force. Its energy is positive. It does not reverse the direction of time around itself. It does not make nearby objects younger. Antimatter has been burdened with enough fictional responsibilities already, without adding those. The question of gravity is a particularly interesting example. For many years, directly testing how antimatter responds to gravity was experimentally difficult because electromagnetic forces are enormously stronger than gravity at the scale of individual charged particles. An antiproton's electric charge means that even tiny stray electric fields can easily overwhelm the gravitational effect researchers would like to measure. This is one reason antihydrogen is so useful. Combine a negatively charged antiproton with a positively charged positron, and the resulting antiatom has no overall electric charge. Scientists can then study how the neutral antimatter system behaves under gravity, with much less interference from electric forces. Experiments with antihydrogen have provided direct evidence that antimatter responds to Earth's gravity in the ordinary downward direction, rather than displaying the fictional tendency to fall upward. This does not mean every detail of antimatter gravity has been measured to unlimited precision. Researchers continue refining the experiments, but the idea that antiprotons possess negative mass and should naturally rise away from Earth is not supported by established physics. The antiproton is the opposite of the proton in specific quantum properties, not in every property one can imagine. Spin creates another source of confusion because the word sounds as though the particle is literally rotating like a small ball. That is not quite right. Spin is an intrinsic quantum property. It behaves mathematically in some ways that resemble angular momentum, but picturing a proton as a tiny solid sphere spinning around its axis can quickly lead to problems. The proton and antiproton possess corresponding spin properties, and this spin contributes to how they interact with magnetic fields. Because both particles are composite, understanding their magnetic behavior in detail involves the motion and spins of their internal quarks, or antiquarks, along with the complicated activity of the strong interaction. Physicists have spent decades investigating how these contributions combine. The proton may be common, but common does not mean simple. One of the great surprises of particle physics has been how difficult it is to explain familiar particles from their internal ingredients alone. We know the fundamental theory describing quarks and gluons remarkably well, yet calculating every feature of a proton from first principles remains challenging because the strong interaction becomes extremely complicated at the energies relevant inside the particle. The antiproton inherits exactly that difficulty. If you want to understand it fully, you're asking the same hard questions asked about the proton, only with the matter content replaced by antimatter content. How is momentum distributed among its constituents? How do the spins of antiquarks and gluons combine? How do temporary quantum fluctuations contribute to measurable properties? How does the strong interaction generate so much of the particle's mass? These are not signs that the theory has failed. They are signs that relatively simple fundamental rules can create extremely complicated collective behavior. We encounter something similar in ordinary life. The rules governing water molecules are well understood. but following every molecule in the ocean during a storm would still be an unreasonable way to plan a picnic. What makes the proton and antiproton pairing so useful is that much of this complexity should mirror perfectly. Whatever complicated contribution the strong interaction makes to the proton's mass, the corresponding antimatter system should produce the same mass for the antiproton. Whatever internal structure gives the proton its magnetic behaviour, the antiproton should display the properly reverse counterpart. The complexity itself becomes part of the test. This is also why the antiproton should not be pictured as less real than ordinary matter. Sometimes the prefix anti makes it sound as though the antiproton is defined only by what it is not. But an antiproton has a complete physical identity. It can exist independently. It can carry momentum across a laboratory. It can be stored for long periods under suitable conditions. It can collide with other particles. It can participate in the strong interaction. It can become bound into larger antimatter systems. If an antiproton encounters an antineutron, the two can interact through the strong force in ways corresponding to interactions between ordinary protons and neutrons. In principle, antimatter nuclei can be assembled. Experiments have produced antideutrons and even heavier antinuclei containing multiple antiprotons and antineutrons. These objects are difficult to create and do not last long in ordinary surroundings, but their existence demonstrates that antimatter can form complex nuclear structures. An antihelium nucleus, for example, is not a mysterious new kind of substance operating under unfamiliar forces. It is the antimatter counterpart of an ordinary helium nucleus. Replace the protons with antiprotons and the neutrons with antineutrons, and the strong interaction can bind the resulting antinucleons together. Add positrons in the appropriate arrangement, and one could in principle form an antihelium atom. If you had a sufficiently large amount of antimatter completely isolated from matter, chemistry based on antiatoms should closely resemble ordinary chemistry. Antihydrogen could participate in electromagnetic interactions because its positron and antiproton carry electric charges that mirror those of the electron and proton. More complicated antiatoms should have corresponding electron-like structures built from positrons. An antimatter chemist, assuming such a being could exist somewhere safely separated from us, would not necessarily find their laboratory unusually exotic. Their antiatoms would interact, their antimolecules could form, and their version of a misplaced cup of coffee would probably remain just as irritating. The problem would begin if that laboratory encountered ours. When a proton and antiproton come close enough to interact strongly, their internal quarks and antiquarks can reorganize and annihilate. This is more complicated than imagining two featureless particles touching and simply turning into light. Because protons and antiprotons are composite objects, their annihilation frequently produces other strongly interacting particles, which then decay into additional particles. The original matter and antimatter identities disappear, but the energy, momentum, and other conserved quantities continue through the products of the reaction. That process reveals why knowing what lies inside the antiproton matters so much. A proton and antiproton annihilation is ultimately an interaction between quarks and antiquarks governed by the strong interaction. The antiproton's internal structure determines how these encounters unfold and what kinds of particles can emerge afterward. The same internal structure also determines how antiprotons are produced in the first place. In a high-energy collision, enough energy must be concentrated to create the necessary quarks and antiquarks, and arrange some of those antiquarks into an antiproton while the rest of the event satisfies the conservation rules. Producing the particle is therefore not like carving an antiproton out of existing material. It is a transformation in which collision energy becomes a new collection of particles, one of which may carry exactly the antiquark structure needed to be recognized as an antiproton. Once created, that antiproton can travel through an accelerator beamline just like any other charged particle. Magnetic fields bend its path because of its negative electric charge. Electric fields can accelerate or decelerate it. Detectors can identify the energy it deposits and the particles produced when it interacts. Carefully designed traps can prevent it from touching the material walls surrounding the experimental chamber. There is something satisfying about the fact that scientists can manipulate an object once considered an unexpected theoretical possibility with such precision. The antiproton began as a consequence of trying to understand the symmetry of fundamental physics. Today, researchers can count antiprotons, guide them through magnetic systems, reduce their speeds, confine them, and compare their properties with those of protons. Yet creating an antiproton remains far more difficult than describing one on paper. There is no natural reservoir nearby from which laboratories can simply collect a useful supply. Each antiproton used in an experiment has to come from a process energetic enough to create it, and only a small fraction of the energy invested in the accelerator ends up stored in the antiparticles scientists actually want. After producing them, researchers then need to separate the antiprotons from a large collection of other collision products and bring them under control without allowing them to strike ordinary matter. Understanding the particle from the inside therefore brings us naturally to the practical question of how one actually obtains it. Knowing that an antiproton contains antiquarks tells us what must be created. Knowing that it has negative electric charge tells us how magnetic and electric fields can guide it. Knowing that it annihilates when it meets ordinary matter tells us why the entire process has to be handled with such care. The physics inside the particle and the engineering required to produce it are closely connected, and following an antiproton from the instant it is born in a violent collision to the moment it becomes a slow, controlled particle in a laboratory reveals just how much work is required to study even one tiny piece of antimatter. Knowing what an antiproton is immediately raises a practical problem. If these particles are so rare in ordinary surroundings, where do physicists actually get them? There is no mine filled with antimatter, no naturally occurring container that can simply be opened, and no convenient cloud of antiprotons drifting above a laboratory waiting to be collected. Antiprotons do appear naturally in energetic processes in space, but collecting useful numbers of them from cosmic rays would be extraordinarily inefficient. If scientists want enough antiprotons to study carefully, they have to create them themselves, and doing that requires recreating a small part of the violent environment in which nature makes new particles. The basic idea begins with energy. A proton is a massive particle, so creating an antiproton requires enough available energy to account for that mass. It is not enough to take an ordinary proton and somehow flip its electric charge. The internal structure must be created as well, including the antiquarks that make an antiproton what it is. In a laboratory, this is accomplished by accelerating ordinary particles to very high speeds, and then colliding them with a matter. The energy concentrated in those collisions can be converted into new particles. Most of the time, the collision produces things physicists are not specifically interested in. Occasionally, if the conditions are right, an antiproton appears among the debris. This is one of the reasons particle accelerators became so important to modern physics. They are not simply machines for making existing particles move quickly. They are also tools for creating particles that are absent from ordinary matter. By increasing the energy of a collision, scientists can open the door to heavier and rarer particle combinations. The accelerator effectively provides nature with enough energy to build things that would otherwise be inaccessible. Imagine throwing two ordinary objects together. At everyday speeds, you expect them to bounce, break, deform, or perhaps leave you wondering why you thought throwing them together was sensible in the first place. At particle accelerator energies, collisions are fundamentally different. The incoming particles carry so much energy that the result can include entirely new particles. The collision does not simply rearrange the original material. Some of the energy becomes mass, while the rest appears as motion and other forms of energy carried by the outgoing particles. This does not mean that anything can appear whenever enough energy is present. Nature still follows strict conservation rules. Electric charge has to balance, momentum has to balance, energy has to balance. Other particle properties must also be accounted for. An antiproton carries negative electric charge, and the antimatter version of the proton's baryon identity, so producing one requires the rest of the collision to compensate appropriately. This is why an antiproton is normally created alongside other particles rather than appearing alone. The process used historically involves accelerating protons and sending them into a target made from ordinary matter. When a fast proton strikes a proton or neutron inside the target, the collision can produce several new particles. If enough energy is available, part of that energy can go into creating a proton and an antiproton pair, along with the other particles needed to keep the reaction balanced. The original collision may look chaotic from the outside, but every allowed event still respects the underlying rules. Producing one antiproton therefore requires significantly more collision energy than simply matching the mass of one antiproton. The rest of the event has to contain enough ordinary matter particles to preserve the relevant conservation laws. This is part of what made the original antiproton search such a technological challenge. Physicists knew what they were looking for, but their accelerators had to become powerful enough to reach the required range before the search could succeed. The machine that finally did this in the 1950s was the Beavertron in California. Its name came from an older way of describing the enormous energies reached by accelerated particles. The machine was specifically capable of accelerating protons to energies high enough that antiprotons could be produced when the beam struck a target. The target itself did not somehow contain hidden antiprotons. It provided particles for the accelerated protons to collide with. In those collisions, the incoming energy was redistributed among many outgoing particles. A tiny fraction of events produced antiprotons. The challenge was then to find them. This is where creating antimatter begins to look less like one experiment and more like a series of increasingly difficult problems. First, the accelerator must produce a sufficiently energetic beam. Then the beam has to strike the target accurately. After that, scientists face a spray of particles emerging from the collision region. The antiprotons are mixed in with far more common particles, many of which carry the same negative electric charge. The researchers must separate the rare particles they want from everything else. Magnetic fields are extremely useful for this because charged particles bend when they travel through them. The direction of the bend depends on whether the charge is positive or negative, while the amount of bending depends on the particle's momentum. By arranging magnets carefully, physicists can create a path that selects negatively charged particles with a particular range of momentum. That already removes many unwanted particles, but it does not solve everything. Electrons are negative. Negative pions and other particles can also be present. An antiproton needs to be identified not just by its charge, but by its mass and speed. This is why particle experiments often use several detectors in sequence. One device may tell researchers when a particle passes a particular point. Another may measure how long it takes to travel between two locations. Another may respond differently depending on the particle's speed. By combining these measurements, scientists can distinguish a slow, heavy antiproton from a much lighter particle carrying similar momentum. The first antiproton experiments required exactly this kind of careful identification. The particles were rare enough that simply seeing a few unusual detector signals was not convincing. The research team had to show that the events matched the properties expected for an antiproton and could not reasonably be explained by known background particles. Particle physics has always had a slightly suspicious personality in this respect. A strange signal is interesting, but everyone wants to know whether a badly behaved detector, an ordinary particle, or some piece of unnoticed equipment is trying to ruin the afternoon. Once antiprotons had been discovered, the problem changed. Physicists no longer had to prove that the particle existed. They wanted to produce larger and cleaner samples so they could measure its properties. That required specialized facilities. Modern antiproton production begins with a powerful accelerator, creating a high-energy beam of ordinary particles, usually protons. Those protons strike a metal target. The collisions produce many secondary particles, including some antiprotons. Magnetic systems collect particles with the correct negative charge and approximate momentum and guide them into a beamline. At this point, however, the antiprotons are moving much too quickly for many precision experiments. High energy was necessary to create them, but it becomes inconvenient once scientists want to study them carefully. Researchers therefore have to slow the antiprotons down. This is much harder than slowing an ordinary object. You cannot put an antiproton into a soft cushion, or let it rub against a surface until it stops. Any ordinary material used for that purpose would contain matter, and contact with matter can destroy the antiproton through annihilation. Instead, scientists reduce the energy of antiprotons using carefully controlled electromagnetic systems. Machines called decelerators perform something close to the opposite job of accelerators. Rather than repeatedly adding energy to a beam, they remove energy in controlled stages. The antiprotons circulate through a machine surrounded by magnets that keep them on the correct path. Electric fields are timed to reduce their energy as they pass through particular regions. With each stage, the beam becomes slower and easier to handle. This sounds straightforward until one remembers that the particles are moving in a beam, whose members are not all perfectly identical. Some antiprotons are slightly faster than others. Their directions vary, their positions spread out. If scientists simply reduce the average speed without controlling that spread, the beam becomes difficult to trap and measure. For that reason, antiproton facilities also use methods known collectively as beam cooling. The word cooling here does not necessarily mean placing the particles near something cold in the everyday sense. It refers to reducing the random spread of their motion so that the beam becomes more orderly. One method measures fluctuations in the particle beam and uses electromagnetic feedback to correct them. Another can use electrons travelling alongside the antiprotons at a carefully chosen speed. Interactions between the particles gradually reduce differences in their motion, leaving the antiproton beam more controlled. The details are technically demanding, but the goal is simple. A wild cloud of fast particles is difficult to study. A narrow, slow, predictable group is much more useful. Eventually, the antiprotons can be brought to energies low enough that individual particles or small groups can be captured in electromagnetic traps. A common device used for charged particles is the Penning trap. It uses electric and magnetic fields together to confine particles in a small region without allowing them to touch the physical walls of the apparatus. The magnetic field controls sideways motion, while electric fields restrict movement in another direction. The result is a particle that can remain trapped in vacuum, moving within an invisible electromagnetic container. This is a rather elegant solution to the antimatter storage problem. The antiproton is surrounded by matter, but ideally it never touches it. The laboratory equipment provides the fields, while the particle itself remains in empty space. Creating the vacuum is also important. Even an apparently empty laboratory chamber contains some stray gas molecules unless air has been removed extremely thoroughly. An antiproton that collides with one of those molecules may eventually encounter a nucleus and annihilate. Researchers therefore create extremely high-quality vacuum conditions so that trapped antiprotons can survive for long periods. Temperature matters too. Slower particles are easier to confine and manipulate, so experimental systems are often operated at very low temperatures. Cooling the equipment also helps improve vacuum conditions because many stray gas molecules stick to cold surfaces rather than wandering through the trapping region. After so much effort, scientists may end up with a quantity of antimatter so tiny that it would be completely invisible to the naked eye. This often surprises people because discussions of antimatter in popular culture tend to involve containers holding dramatic glowing quantities of the stuff. Real laboratories work with vastly smaller amounts. Producing antimatter is extremely inefficient. An accelerator consumes an enormous amount of energy to operate. Only part of that energy reaches the incoming beam. Only a fraction of the collisions produce antiprotons. Only some of those antiprotons travel in useful directions. Only some can be captured and slowed. By the end of the process, the amount of antimatter stored represents an almost absurdly small fraction of the energy originally used. This is why antimatter is not a practical energy source. Antimatter can release a large amount of energy when it annihilates with matter. But first, you have to make the antimatter. Producing it costs far more energy than you could recover from using it later. Calling antimatter a source of energy is therefore slightly misleading. It would be more accurate to think of it as a very expensive way of storing energy, with the added inconvenience that the storage container cannot actually touch what it stores. For scientific research, efficiency is not the main goal. Scientists do not produce antiprotons because they want electricity from them. They produce antiprotons because even a small number can answer important questions. Some experiments compare antiprotons directly with protons. A trapped antiproton can be made to move in a magnetic field, and its response can reveal properties such as the ratio between its charge and mass. Other experiments examine its magnetic behavior. By performing matching measurements on ordinary protons, researchers can test whether the two particles obey the expected matter and antimatter symmetry. These are extraordinarily precise experiments. A large difference would have been noticed long ago. The interesting possibility now lies in differences so tiny that detecting them requires extreme control of magnetic fields, temperatures, particle motion, and detector noise. The antiproton may spend weeks or months behaving perfectly normally before physicists extract another decimal place of information from it. A second use for laboratory antiprotons is the creation of antihydrogen. To make an antihydrogen atom, scientists need an antiproton and a positron. Positrons are much easier to produce than antiprotons because they are far lighter and arise naturally in several radioactive and high-energy processes. Researchers first prepare clouds of antiprotons and positrons inside electromagnetic traps. They then bring the two species together under carefully controlled conditions. Occasionally, a positron becomes bound to an antiproton, producing neutral antihydrogen. The fact that antihydrogen has no overall electric charge creates a new problem. The electromagnetic traps used for charged antiprotons cannot hold a neutral antiatom in the same way. Instead, scientists exploit the tiny magnetic properties of antihydrogen and create specially shaped magnetic fields that can confine some of the newly formed atoms. Only antihydrogen atoms with sufficiently low energy can be trapped. Faster ones escape and eventually strike the material walls, where they annihilate. This means researchers must make the antiatoms cold enough from the beginning, which adds yet another layer to an already delicate process. When trapped antihydrogen eventually annihilates against the apparatus, detectors surrounding the experiment can observe the particles produced in the event. These annihilation signals allow researchers to determine where and when the antihydrogen disappeared. In some experiments, scientists deliberately release the trapped antiatoms and study how they move before annihilating. The ability to produce and hold antihydrogen has allowed experiments that would have sounded almost impossible when the antiproton was first discovered. Researchers can shine carefully chosen light on antihydrogen and investigate whether it responds at the same frequencies as ordinary hydrogen. They can examine its gravitational behavior. They can test whether the antimatter atom follows the same basic physical rules as its matter counterpart. All of this begins with the rather brutal process of smashing a high-energy proton beam into a target. There is a striking contrast between the beginning and end of the procedure. At the start, antiprotons are born in violent collisions producing showers of particles. The environment is energetic, fast and messy. At the end, the successful experiment may involve a single antiproton moving quietly inside a cryogenic electromagnetic trap, while physicists measure tiny changes in its motion. The entire laboratory process is an exercise in reducing chaos. First, you produce enormous numbers of collisions, then you select the rare antiprotons, then you separate them from other particles, then you slow them down, then you cool the beam, then you trap the particles, then finally you ask them a very careful question. One might reasonably wonder how scientists know an antiproton has been trapped if they cannot simply look at it. The answer comes from the electrical signals produced by its motion. A charged particle moving inside a trap can induce extremely small currents in nearby electrodes. Sensitive electronics detect those signals, allowing researchers to determine properties of the particle without destroying it. This is sometimes called non-destructive detection. Instead of waiting for the antiproton to annihilate and examining the remains, scientists can monitor its motion while keeping it alive. That makes long precision measurements possible. Eventually, of course, some experiments do rely on annihilation. An antiproton can be deliberately released into ordinary matter, and detectors record the resulting particles. These events are useful because annihilation produces a distinctive signature. The antiproton effectively announces that it has reached the wall by producing a small burst of secondary particles. The remarkable thing is that laboratories can repeat this process reliably. Antiprotons are not unpredictable visitors appearing at random. They can be produced in scheduled accelerator runs, collected, stored, transferred between experimental systems and measured. Researchers have even developed methods for transporting trapped antiprotons between different locations. The trap itself can be designed as a carefully protected electromagnetic container, surrounded by equipment that maintains the magnetic field and vacuum conditions during transport. Moving antimatter through a building sounds like something requiring dramatic warning lights and a heroic soundtrack, but the actual quantity is so small that the main danger is usually to the experiment rather than to the building. If the trap fails, the antiprotons annihilate against ordinary material, and the researchers lose their precious sample. Nothing resembling a cinematic explosion follows. There simply is not enough antimatter present. This enormous gap between fictional quantities and laboratory quantities is worth keeping in mind. Humanity has learned how to make antimatter, but not in amounts that could fill a bottle or power a vehicle. The total quantities involved in experiments are microscopic beyond ordinary experience. Even accumulating a visible speck of antiprotons would require production far beyond anything currently practical. The scientific importance of those tiny samples, however, is enormous. Every antiproton created in an accelerator carries a version of the same fundamental structure found in ordinary protons throughout the universe. By producing and isolating it, physicists gain access to a controlled piece of antimatter that can be compared directly with matter. This laboratory control also removes much of the uncertainty that comes with studying antimatter in space. Cosmic antiprotons arrive after travelling through complicated astrophysical environments. Their origins may not always be obvious. In a laboratory, researchers know how the antiprotons were produced, what fields they have passed through, how their energies changed, and what conditions surround them. That allows tests of extraordinary sensitivity. If the proton and antiproton differ in some hidden way, a carefully trapped particle may reveal it. If antihydrogen responds unexpectedly to light or gravity, laboratory experiments can measure the deviation. If every measurement continues to agree with current theory, the result pushes possible new physics into an even narrower region. The irony is that the better scientists become at producing antimatter, the more carefully they try to prevent it from doing the thing antimatter is most famous for. Annihilation is easy. Preservation is difficult. Once an antiproton exists, the challenge is keeping it away from the almost unlimited supply of ordinary matter surrounding the experiment. Yet annihilation itself is not merely an inconvenience, it is also one of the richest sources of information about the antiproton. When a proton and antiproton finally meet, the interaction reveals what happens when a composite matter particle encounters its composite antimatter counterpart. Their quarks and antiquarks do not simply disappear in one clean flash. The strong interaction rearranges their energy into a collection of new particles, and the details of that process tell us a great deal about how matter and antimatter are connected. After all the accelerators, targets, magnets, decelerators, vacuum chambers, and traps required to bring an antiproton under control, the most natural thing to examine next is the event researchers spend so much effort preventing. what actually happens when the proton and its antimatter twin are finally allowed to meet. Once an antiproton has been created, slowed, and carefully kept away from ordinary matter, a rather obvious question remains. What happens when we stop protecting it? After all, the most famous property of antimatter is what occurs when it finally meets matter. A proton and an antiproton can exist separately without anything particularly dramatic happening. Put enough distance between them and each simply behaves as a particle. Bring them together closely enough, however, and the situation changes completely. The proton contains quarks. The antiproton contains the corresponding antiquarks. When those two composite particles interact through the strong force, their original identities can be converted into a collection of new particles. This process is called annihilation, and although the name suggests something simply vanishing, the actual event is considerably busier. Annihilation does not mean that the proton and antiproton disappear and leave an empty patch of space behind. Physics does not allow their energy to be casually thrown away. The energy that was carried in their mass and motion remains present, but it is redistributed into other particles. Momentum also has to be conserved, along with the other quantities required by the interaction. What disappears is the original arrangement that allowed us to call one object a proton and the other an antiproton. The ingredients and energy are reorganized into something else. This is easier to understand if we remember that neither particle is elementary. A proton is made mainly from 3 quarks, surrounded by the complicated activity of gluons and additional temporary quark and antiquark contributions. An antiproton contains the corresponding 3 antiquarks and its own strong interaction activity. When the particles meet, we should therefore not imagine 2 perfectly smooth spheres touching and immediately turning into a neat flash of light. Their internal constituents become involved in a strong interaction that can produce several new particles. A proton and an antiproton carry opposite versions of important particle properties, so together they form a system in which those properties can balance. Their quarks and antiquarks can annihilate or rearrange through the strong interaction. The energy available in the event is then commonly carried away by particles known as mesons. Mesons are themselves made from a quark and an antiquark, and several different kinds can appear depending on the details of the annihilation. Among the most common products are particles called pions. Pions come in charged and neutral varieties and do not survive indefinitely. They decay into other particles. Neutral pions tend to decay extremely quickly into high-energy photons, while charged pions generally produce other particles through their own decay chains. By the time an experimental detector has finished recording everything, a single proton and antiproton meeting may have produced a small family tree of secondary particles. This is why saying that matter and antimatter turn directly into light is an oversimplification. Electron and positron annihilation can often produce photons in a comparatively clean way, especially when the particles meet under simple conditions. Proton and antiproton annihilation is messier because protons and antiprotons have internal structure. Their quarks participate in the interaction, and the strong force tends to produce hadrons before those particles continue through additional decays. From the perspective of a detector, the event can look like several particle tracks spreading away from one point. Scientists reconstruct those tracks and measure their energies to work out what happened. The place where the antiproton met ordinary matter becomes visible not because the antiproton itself can be seen, but because of the collection of products that leaves the interaction. This is extremely useful in antimatter experiments. If researchers are trapping antiprotons or antihydrogen, they need to know when the antimatter has escaped and touched the walls of the apparatus. Annihilation provides a convenient signal. Detectors surrounding the experiment can record the secondary particles and reconstruct the approximate location where the event occurred. So the very process scientists work hard to prevent can also become one of their best detection methods. While the antiproton is safely trapped, researchers can measure it without destroying it. Once it escapes, its annihilation announces its departure rather clearly. The amount of energy released in matter and antimatter annihilation has given antimatter its dramatic reputation. When ordinary matter is burned chemically, only a tiny fraction of the total energy stored in its mass becomes available. Most of the mass remains in the products. When matter and antimatter annihilate, a much larger fraction of the original rest mass can be transformed into the energy and mass of other particles that may eventually end up as radiation and lighter particles. That makes antimatter sound like the perfect fuel until we remember where the antimatter came from. If you want an antiproton, you have to spend energy creating it. Current methods are extraordinarily inefficient. Particle accelerators consume vastly more energy than could ever be recovered from the tiny amounts of antimatter they produce. The annihilation may be energetic, but the overall process is not a free source of power. There is also very little antimatter available in laboratories. The quantities are so small that an accidental loss of a trapped sample is a scientific disappointment rather than a threat to the surrounding city. A handful of antiprotons touching the walls of a trap produces detectable particles, not an explosion that requires anyone to dramatically run down a corridor. This difference between the microscopic event and fictional portrayals is important. At the scale of individual particles, annihilation is extremely energetic compared with many other particle interactions. At the scale of human objects, the amount of antimatter we can actually produce and store is tiny beyond everyday imagination. The reason annihilation is so fascinating is not really the amount of energy involved. It is what the process reveals about the relationship between matter and antimatter. A proton is one of the most stable objects in ordinary matter. Left alone, it appears capable of surviving for an extraordinarily long time. An antiproton is equally stable when isolated from matter, yet when the two encounter each other, neither needs to remain a proton or antiproton. Their combined quantum properties allow the system to transform into new particles. This tells us something important about what a particle is. A proton is not a permanent piece of substance that has to remain a proton forever, simply because it began as one. Particle identity depends on the arrangement of fields, energy, and quantum properties. During an allowed interaction, that identity can change while the deeper conservation rules remain respected. If you imagine a proton as a tiny indestructible marble, annihilation seems impossible. Two marbles can collide, but each marble should still exist afterward. If instead you think in terms of quantum fields and allowable particle states, annihilation becomes much less mysterious. The energy associated with a proton and antiproton can be reorganized into other excitations of those fields. The universe is not destroying its ingredients, it is changing the form in which they appear. This is one reason modern particle physics feels so different from the mechanical world of ordinary objects. A chair may break into smaller pieces, but we do not expect it to collide with an anti-chair and become a shower of new furniture. At the particle level, creation and annihilation are normal features of the theory. The word annihilation can also create the impression that matter always aggressively seeks out antimatter. It does not. A proton and antiproton separated by a large distance will not suddenly leap across a laboratory toward one another simply because they are opposites. Their electric charges do attract because one is positive and the other is negative, but that is an ordinary electromagnetic interaction. An electron is also attracted to a proton, and the result is usually a hydrogen atom rather than annihilation because the electron is not the proton's antiparticle. For proton and antiproton annihilation to occur, the particles have to approach closely enough for the relevant interactions to take place. If an antiproton enters ordinary matter, that usually does not take long. Matter is filled with nuclei, and those nuclei contain protons and neutrons. The antiproton can lose energy as it travels through material and eventually become captured near a nucleus. Once it reaches the nuclear region, the strong interaction makes annihilation highly likely. This behavior has even allowed antiprotons to be used as probes of nuclear structure. By observing how antiprotons interact with different nuclei, researchers can learn about the distribution of protons and neutrons near the edges of those nuclei. The antiproton is destroyed in the process, but its final interaction carries information about the matter it encountered. There is a slightly unusual logic to many particle physics experiments. A scientist may spend considerable effort creating a rare particle, carefully guide it through a machine, measure it, and then deliberately allow it to be destroyed because the destruction itself provides useful data. It is not an especially relaxing career if one becomes emotionally attached to the particles. Annihilation also plays an important role when scientists work with antihydrogen. An antihydrogen atom contains an antiproton and a positron. Because the total electric charge of the atom is neutral, antihydrogen cannot be confined using exactly the same electric traps used for a bare antiproton. Instead, carefully arranged magnetic fields hold sufficiently cold antiatoms. If the trapping fields are changed and an antihydrogen atom escapes, it eventually reaches ordinary material. The positron can annihilate with an electron, while the antiproton can annihilate within an atomic nucleus. Detectors then record the resulting signals. By determining where those annihilations occur, scientists can work backward and learn how the antihydrogen moved before it touched the apparatus. This has become especially useful in experiments studying gravity. If antihydrogen is released from a trap, researchers can examine whether the antiatoms tend to move downward under Earth's gravitational field in the way ordinary matter does. Because the antihydrogen disappears as soon as it reaches the material walls, annihilation provides the final marker of its path. The idea of using destruction as a measurement may sound strange, but detectors frequently work this way. We often learn about unstable or difficult particles from what they become, rather than by watching the original particles directly. Particle physics is full of brief visitors whose existence has to be reconstructed from the traces they leave behind. The energy produced in proton and antiproton annihilation also helps scientists understand the strong interaction itself. Because the interaction produces combinations of mesons and other particles, the frequencies and patterns of those products test models of how quarks and gluons reorganize. Different collision energies and conditions reveal different aspects of the process. When the proton and antiproton are moving very slowly before annihilation, the event explores one kind of strong interaction environment. When they collide at very high energies, the picture becomes different. High-energy proton and antiproton colliders were once major tools for particle physics because the collision energy could create entirely new heavy particles. One famous example was the Proton and Antiproton collider at CERN that operated during the 1980s. Rather than allowing slow protons and antiprotons to annihilate after drifting together, the machine accelerated beams of both to enormous energies and sent them into head-on collisions. The energy of motion was then available for producing much heavier particles. Those experiments contributed to the discovery of particles responsible for the weak interaction, providing a major confirmation of the developing standard model. Here the antiproton was useful not merely because it could annihilate with a proton, but because the combination of particle and antiparticle made certain high-energy collision processes especially effective for producing the signals physicists wanted. Later colliders also used proton and antiproton beams. The Tevatron in the United States became one of the world's most important particle accelerators and contributed to major discoveries, including the top quark. Producing and storing enough antiprotons for a collider was an enormous technical challenge because a high-energy experiment requires a useful beam rather than one carefully isolated particle. This gives the antiproton two very different experimental lives. In one laboratory, a researcher may spend days studying a single trapped antiproton with exquisite precision. In another type of experiment, enormous numbers of protons and antiprotons can be accelerated into collisions so energetic that scientists are interested mainly in what new particles emerge from the wreckage. Both approaches depend on the same basic physical fact. A proton and antiproton bring together matter and antimatter in a system whose combined energy can be transformed into other particle states. There is another important detail. Annihilation is not restricted to a proton meeting an antiproton. An antiproton can also annihilate when it interacts with a neutron inside an atomic nucleus, because the underlying quark and antiquark content allows strong reactions that remove the original antiproton and nucleon and produce mesons. The exact products depend on the particles and conditions involved. This is why an antiproton entering ordinary matter is unlikely to survive merely because it happened to avoid every proton. Atomic nuclei also contain neutrons, and the strong interaction provides plenty of opportunities for the antiparticle to disappear into a new set of products. At first, all of this might make antimatter seem hopelessly fragile, but fragility is not quite the right word. The antiproton itself is not unstable. It does not decay simply because time passes. Its difficulty comes from the environment. Place an antiproton in ordinary matter, and it has many possible annihilation partners. Place it in a sufficiently good vacuum and keep it away from material surfaces, and it can persist. That distinction matters enormously. If antiprotons automatically decayed after a tiny fraction of a second, precision experiments would be much harder. Instead, physicists can preserve them long enough to perform careful measurements. Antimatter is therefore not fleeting because it is internally defective. It is fleeting in our surroundings because our surroundings are made of the opposite kind of material. Imagine living in a world made almost entirely from antimatter. An antiproton inside an antihydrogen nucleus would not seem dangerous there. It could remain associated with a positron and behave as part of an ordinary anti-atom. An antimatter laboratory containing antimatter walls would not cause antiprotons to annihilate simply because they touch the equipment. From that perspective, a proton arriving from our world would be the troublesome visitor. This is a useful reminder that the terms matter and antimatter partly reflect which side happens to dominate our environment. We call protons ordinary because they are everywhere around us. We call antiprotons exotic because they are rare here. The underlying laws do not appear to assign moral importance to either side. That brings us back to the larger puzzle. If protons and antiprotons can annihilate so efficiently, what happened when the early universe contained both in enormous numbers? At very high temperatures, particles and antiparticles could be created repeatedly from energetic interactions. A proton could meet an antiproton and annihilate, while elsewhere enough energy could produce new particle and antiparticle pairs. The early universe was therefore not a quiet collection of permanent particles. It was a rapidly changing environment in which creation and destruction occurred continuously. As expansion caused the universe to cool, producing heavy particle pairs became increasingly difficult. Annihilation continued, but replacement could no longer keep pace. Protons and antiprotons encountered one another and disappeared into other particles and radiation. If the numbers of matter and antimatter particles had been exactly equal, the process could have continued until almost nothing remained of either population. There would still have been radiation and other particles, but the large structures built from surviving ordinary matter would not have developed in the way we observe today. Somehow, there were slightly more matter particles. The excess was tiny compared with the original population, but after nearly all the matching matter and antimatter pairs annihilated, that small surplus remained. Every ordinary proton in the modern universe may therefore be thought of as part of the leftover population that had no antiproton partner available when the great early period of annihilation ended. The table beside you, the atmosphere, the planet beneath you, and the stars visible across the galaxy are made from those survivors. This is what gives proton and antiproton annihilation such unusual significance. In a laboratory, it is a microscopic interaction lasting an unimaginably short time. In cosmology, the same basic process helped determine what kind of universe remained after the earliest hot conditions had passed. And it leaves us with an uncomfortable question. If matter and antimatter are produced according to such closely matched rules, why was there any surplus at all? One possible clue lies in subtle differences between how matter and antimatter behave in certain particle interactions. Physicists have observed some of those differences, but the known effects do not yet provide a complete explanation for the amount of matter we see today. Something about the early universe still seems to be missing from the story. That is why scientists continue testing antiprotons with such precision. They are looking for any small departure from the expected symmetry that might reveal a deeper imbalance. Perhaps the antiproton and proton will continue matching every test indefinitely. Perhaps a future measurement will expose a difference so small that earlier experiments could not see it. Either outcome teaches us something. Before those comparisons can be pushed further, researchers face the practical challenge that has followed antimatter science from the beginning. An antiproton is useful only while it can be controlled, and ordinary matter surrounds every experiment. Keeping the particle away from the apparatus, slowing it enough for delicate measurements, transporting it without loss, and sometimes combining it with positrons requires technology almost as interesting as the particle itself. The next step is therefore not another collision but the opposite problem entirely, learning how to catch something that must never be allowed to touch the container holding it. The problem with catching an antiproton is that almost everything you could normally use to catch something is made from exactly the material you need to keep away from it. Put a marble in a glass jar and the marble can rest against the glass. Put water in a cup and the water can touch the cup. Try the same basic approach with an antiproton and the container becomes part of the experiment in a rather inconvenient way. The walls contain atoms, the atoms contain nuclei, and the nuclei contain protons and neutrons. If the antiproton reaches that material, it can annihilate. Scientists therefore have to build a container whose most important feature is that the thing being stored never actually touches it. This sounds like a contradiction until we remember that an antiproton carries electric charge. Because its charge is negative, electric and magnetic fields can push, pull, guide, and confine it without making physical contact. Instead of placing the antiproton inside a little material box, researchers place it inside a carefully shaped region of electromagnetic fields. The walls of the apparatus remain safely outside the particle's path, while the invisible fields do the actual work of holding it in place. One of the most important devices for doing this is called a penning trap, a tool that has become central to some of the most precise measurements ever made on antiprotons. A penning trap combines a strong magnetic field with carefully arranged electric fields. The magnetic field prevents the charged particle from simply flying sideways out of the trap, while the electric fields restrict its motion along the remaining direction. The antiproton does not sit perfectly motionless in the center. It moves in characteristic patterns within the trap, circling and oscillating while remaining confined to a small region. Those motions may sound like an inconvenience, but they are actually useful. By observing them with extraordinary accuracy, scientists can learn about the antiproton itself. Before any of this can happen, however, the antiproton has to arrive slowly enough to be captured. The particles produced in high-energy collisions are initially far too energetic for precision trapping. At CERN, antiprotons are produced when a high-energy proton beam strikes a metal target. The resulting collisions create many secondary particles, including antiprotons. Magnetic equipment selects some of the useful antiprotons and sends them toward the antiproton decelerator, a machine whose job is almost the reverse of what its name as an accelerator facility might lead you to expect. Instead of giving the particles more and more energy, it progressively removes energy from them while cooling the beam and bringing its motion under better control. A second machine called ELINA slows the antiprotons further, making it possible for experiments to capture far more of them than would otherwise survive the transition into traps. The word cooling needs a little explanation here because particle physicists use it differently from the way we normally talk about cooling a drink. A beam can contain particles travelling roughly in the same direction, while still having a large spread in their individual speeds and sideways motion. Such a beam is considered relatively hot. Cooling the beam means reducing that random spread so the particles move in a more organised and predictable way. A colder antiproton beam is easier to focus. easier to transfer, and much easier to capture. This may seem like a strange sequence of events. Scientists begin by using an enormous accelerator complex to create antiprotons through extremely energetic collisions. Then, having finally made them, they devote another collection of sophisticated machines to removing most of that energy. It is rather like building a powerful catapult because you urgently need an object on the other side of the room, then realizing your actual experiment requires the object to arrive gently enough to balance on a saucer. Unfortunately, antiprotons do not respond particularly well to requests to slow down on their own. Once the antiprotons have been decelerated, an experiment can capture them using electromagnetic fields. The transfer has to be carefully timed. The electric potential inside the trap is adjusted so that incoming particles can enter, after which the field configuration changes and closes the electromagnetic door behind them. Nothing physical swings shut. The fields simply change in a way that prevents the antiprotons from escaping along the direction they arrived. All of this takes place inside an extremely good vacuum. Even air is a problem, because air contains molecules made from ordinary matter. If enough stray molecules remained inside the trap, an antiproton could eventually collide with one of them and be lost. Pumps remove as much gas as possible, and the trapping apparatus is often kept at very low temperatures. Cold surfaces help capture residual gas molecules that might otherwise wander into the region where the antiprotons are stored. The result is an environment that is emptier than almost anything we encounter naturally at ground level. Somewhere inside that near vacuum, a particle smaller than anything visible is circling inside fields produced by equipment that may occupy a substantial part of a laboratory. The difference in scale is impressive. An entire experimental system of magnets, electrodes, electronics, cooling equipment, vacuum chambers, computers, and shielding can exist primarily to keep one antiproton from touching anything. Scientists do not necessarily work with only one antiproton at a time, however. Some experiments maintain a reservoir containing a larger group and extract individual particles when measurements are required. The base experiment at CERN uses a system of several penning traps with different jobs. One stores antiprotons for future use, another is designed for precision measurements, another helps determine the particle's spin state, and a cooling trap prepares particles for measurements requiring exceptionally well-controlled motion. BASE has demonstrated antiproton storage lasting hundreds of days, allowing experiments to continue working with captured antiprotons even during periods when fresh accelerator beam is unavailable. Keeping antiprotons for that long tells us something easily forgotten about antimatter. The antiproton is not inherently eager to disappear. If it were fundamentally unstable, no trap could save it. The reason antiprotons usually have short lives in ordinary surroundings is simply that ordinary surroundings are full of matter. Remove that matter and control the particle electromagnetically, and an antiproton can remain available for experiments for a surprisingly long time. The next challenge is knowing what the trapped particle is doing. Researchers cannot place a tiny camera beside it. Light is also not necessarily the best way to monitor a single charged particle in this kind of experiment. Instead, the motion of the antiproton itself generates an extremely small electrical signal in the trap electrodes. Sensitive electronics can detect this induced current without forcing the antiproton to annihilate. The signal allows scientists to infer how the particle is moving while leaving it safely trapped. This non-destructive detection is extremely important. If every measurement required destroying the antiproton, researchers would constantly need fresh particles. Instead, the same trapped particle can be observed repeatedly. Its motion can be measured, adjusted, cooled, transferred between different sections of the apparatus, and measured again. A single antiproton can therefore become the subject of a remarkably long experimental relationship. The frequency of its motion in the magnetic field carries information about the relationship between its electric charge and its mass. A proton can be measured under comparable conditions, allowing scientists to ask whether the two particles match as precisely as fundamental symmetry says they should. Modern experiments have compared these properties to extraordinary precision and have found no difference beyond the expected reversal of electric charge. BASE has reported comparisons of the proton and antiproton charge to mass relationship reaching uncertainties of only a few tens of parts per trillion. That level of precision can be difficult to picture. A part per trillion is such a small fraction that ordinary comparisons become slightly ridiculous, but that is exactly the territory precision particle physics occupies. Researchers are no longer asking whether the proton and antiproton are roughly the same mass. They're asking whether a difference might be hidden many decimal places deeper than anything a direct everyday measurement could reveal. The magnetic properties of the antiproton provide another test. Protons and antiprotons behave like tiny magnets because of their spin and internal structure. A trapped antiproton placed in a magnetic field has different possible spin orientations. Researchers can induce transitions between those states and detect the resulting changes through the particle's motion. By repeating the process under tightly controlled conditions, they can determine the antiproton's magnetic moment and compare it with that of the proton. This is a demanding measurement because the magnetic signal associated with a single antiproton is extremely small. The particle also has to be cold enough that random motion does not hide the subtle change scientists are trying to detect. A particle that is moving too energetically inside the trap creates too much uncertainty. Researchers therefore spend considerable effort preparing individual antiprotons in exceptionally low energy states before the most sensitive measurements begin. The process can involve moving one antiproton back and forth between specialized traps. One region may be better for determining its spin state, while another provides a cleaner magnetic environment for measuring its motion. A separate cooling region can reduce unwanted energy before the particle is sent back for another attempt. Rather than asking one piece of equipment to do everything at once, the experiment divides the work among traps designed for different purposes. This arrangement resembles a very unusual scientific production line. An antiproton leaves the reservoir, enters a region where its motion is prepared, moves into a measurement trap, perhaps returns for further cooling, and then undergoes another measurement. The difference is that the entire production line may be concerned with one particle, and nobody wants the product to reach the factory wall. The environment has to remain remarkably stable throughout this process. If the magnetic field changes slightly because of nearby equipment, temperature variations, or activity elsewhere in an accelerator facility, the measurements can be disturbed. This becomes increasingly important as experiments grow more precise. Eventually, the surrounding laboratory itself can become part of the limitation. That problem has led to an idea that would once have sounded rather bold. Instead of requiring every precision antiproton experiment to remain permanently beside the machine that produces the antiprotons, why not trap the particles and carry them somewhere quieter? For years, producing antiprotons and studying them were closely tied to the same specialized facilities because transferring antimatter outside a fixed apparatus was extremely difficult. The particle has to remain trapped continuously, meaning the magnetic field, vacuum, cooling, electrical control and monitoring systems all have to travel with it. A portable antiproton trap is therefore not a small container in the ordinary sense. It is a complete life support system for antimatter. The BASE collaboration developed a transportable system called BASE STEP for exactly this purpose. It uses a cryogenic penning trap together with superconducting magnets, a vacuum chamber, electrical control systems, and independent power support. The apparatus weighs around a ton, which is wonderfully typical of particle physics. The object being transported is microscopic, while the container requires something closer to industrial moving equipment. In March of 2026, CERN reported that the BASE team had successfully transported a trap containing antiprotons across the laboratory's main site. The team accumulated 92 antiprotons in the portable cryogenic penning trap, disconnected the system from the main experimental facility, loaded it onto a truck, moved it across CERN, and continued operating the experiment afterward. It was an important demonstration that trapped antimatter could remain under control even while the entire apparatus experienced the ordinary disturbances of transportation. The achievement is more scientifically useful than the simple idea of driving antimatter around might suggest. Precision measurements are affected by the electromagnetic environment surrounding accelerator equipment. Moving trapped antiprotons into specially designed laboratories away from that noise could allow researchers to perform measurements under quieter and more stable conditions. Transport could also eventually allow antiprotons produced at one facility to be delivered to other laboratories equipped to study them. The challenge during such a journey is not primarily the danger posed by the antimatter. The amount involved is far too small to produce a significant explosion. The real concern is keeping the sample alive. The trap must preserve its strong magnetic field. The superconducting magnet has to remain cold. The vacuum must remain extremely clean. Electrical systems must continue controlling the particles. Vibrations and acceleration from movement must not shake the antiprotons out of confinement. In a strange way, the antiprotons themselves are among the least troublesome passengers. They do not know they are travelling in a truck. If the electromagnetic environment surrounding them remains stable, they continue moving inside their trap exactly as before. It is the machinery around them that has to cope with the road. The ability to move antiprotons could change the kinds of experiments researchers perform. A laboratory designed exclusively for precision measurement could be placed far from the disturbances associated with particle accelerators. Antiprotons could be created at CERN, captured, transported, and then studied in an environment chosen specifically for magnetic stability. This could improve comparisons between matter and antimatter and make extremely subtle differences easier to search for. Other experiments are interested in using trapped antiprotons for very different reasons. Rather than measuring the antiproton itself, researchers can use it as a probe of atomic nuclei. An antiproton introduced into a nucleus eventually annihilates with one of the nucleons near the nuclear surface. By studying the particles produced, scientists can learn about the distribution of protons and neutrons in unusual nuclei. This is especially useful for exotic radioactive nuclei that exist for only short periods. Such nuclei may have unusual structures, including extended clouds of neutrons or protons near their outer edges. Normally it is difficult to transport these short-lived nuclei to a distant antiproton facility before they decay. A project called PUMA approaches the problem from the opposite direction by developing a transportable antiproton system intended to bring the antiprotons to the exotic nuclei instead. This gives us a useful sense of how flexible the antiproton has become as an experimental tool. The first challenge was simply proving it existed. Later researchers learned how to produce usable beams. Then they slowed those beams, captured antiprotons, stored them for long periods, measured individual particles, and began designing ways to transport them. The same object that once appeared only as a rare product in a violent collision can now be treated with extraordinary control. There is still an important difference between control and abundance. Scientists can manipulate antiprotons precisely, but they cannot make large quantities cheaply. Every trapped sample represents the end of a long chain, beginning with high-energy proton acceleration and continuing through target collisions, particle selection, deceleration, cooling, transfer, and capture. Losing the sample may not be dangerous, but it wastes a considerable amount of experimental effort. This is another reason reservoir traps are so valuable. Instead of relying on a new delivery of antiprotons every time a measurement is performed, researchers can store a supply and extract them gradually. If the accelerator temporarily stops providing antiprotons, precision experiments can continue using particles already held in reserve. The idea of a reservoir full of antimatter sounds more dramatic than the reality. We are still talking about microscopic quantities. There is no glowing tank. There is a vacuum chamber surrounded by magnets and electronics, containing a number of particles so small that their presence has to be inferred from tiny electrical signals. Yet from the point of view of fundamental physics, even a single well-controlled antiproton can be more valuable than an enormous amount of ordinary material. A kilogram of ordinary matter contains a hopelessly large number of protons for anyone hoping to study them individually. Their collective behaviour is useful for chemistry and materials science, but precision particle experiments often benefit from the opposite approach. Remove nearly everything, isolate one particle, control its motion, measure it over and over again until there is nowhere left for an unexpected difference to hide. This ability to work with individual antiprotons has turned matter and antimatter comparisons into some of the sharpest tests of modern physics. So far, the mirror continues to hold. The antiproton's mass and charge relationship agrees with the corresponding proton measurement to astonishing precision. Its magnetic behaviour continues to follow the expected antimatter pattern. Each improvement reduces the space available for hidden differences. There is something slightly frustrating about that success because the universe still appears to contain vastly more matter than antimatter. The experiments tell us that an antiproton looks remarkably like the proton's perfectly matched counterpart. Cosmology tells us that the two counterparts did not somehow survive in equal numbers. The better the laboratory symmetry becomes, the more peculiar the cosmic asymmetry begins to look. Perhaps there are differences hidden beyond present precision. Perhaps the explanation lies in other particles and interactions rather than in the proton and antiproton themselves. Perhaps events in the earliest moments of the universe created an imbalance through processes that no modern laboratory has yet reproduced. Whatever the answer turns out to be, trapping antiprotons allows scientists to keep checking one of the most obvious possibilities, rather than merely assuming that matter and antimatter are identical where theory expects them to be. And while physicists have become remarkably good at keeping a few antiprotons alive inside electromagnetic traps, nature presents us with the opposite situation on the larger scales. Space is vast, mostly empty, and filled with energetic environments capable of creating antiparticles. Cosmic rays produce antiprotons. Violent astrophysical events produce particles at energies far beyond ordinary terrestrial conditions. The laws of physics seem perfectly willing to make antimatter whenever the circumstances allow it, which makes the absence of large amounts of antimatter around us increasingly difficult to ignore. Once we leave the laboratory and look outward, the question is no longer how to keep an antiproton from touching matter, but why the universe seems to have left so few antiprotons for us to find. If the laboratory teaches us that antiprotons can exist perfectly well when they are kept away from ordinary matter, then the universe presents a much larger and more difficult question. Space is enormous. Most of it is far emptier than any room on Earth. There are energetic cosmic rays, exploding stars, violent magnetic fields, hot gas, black holes, and collisions energetic enough to create particles that would never appear in ordinary conditions. Nature clearly has the ability to produce antimatter, including antiprotons. We know this because antiprotons have actually been detected arriving in cosmic rays. They are out there. The puzzle is that they appear in relatively small numbers, while protons seem to be almost everywhere. Once we recognise how closely the proton and antiproton mirror one another in the laboratory, the imbalance across the universe becomes difficult to ignore. The simplest place to begin is with the matter around us. Earth is made from ordinary matter. Its rocks contain nuclei built from protons and neutrons. The oceans, atmosphere, plants, animals, buildings, satellites, and everything else we routinely encounter follow the same pattern. The moon is matter. Samples returned from its surface behave exactly as ordinary matter should. Meteorites that fall to Earth are matter. Spacecraft have travelled through the solar system without encountering regions where large amounts of antimatter appear to be waiting. The sun is made overwhelmingly from ordinary matter as well, with protons participating in the nuclear reactions that power it. From our immediate surroundings, there is no sign that matter and antimatter were distributed equally and simply happened to occupy different streets. Move farther away and the same general picture continues. the gas between stars behaves as ordinary matter. Stars interact with surrounding material without showing the enormous annihilation signatures that would be expected if many of them were composed of antimatter. Galaxies contain gas, dust, stars, planets, and other structures that seem to be built from ordinary particles. Across the observable universe, matter appears to dominate. That does not mean every individual object has been opened up and checked. Astronomers cannot travel to a distant galaxy and remove a sample to see whether its nuclei contain protons or antiprotons. Much of astronomy works by examining light and other forms of radiation arriving across space. This creates an interesting complication, because an antimatter star could look surprisingly normal from a great distance. Imagine a star made from antihydrogen and antihelium. Instead of protons, it would contain antiprotons. Instead of electrons, its atoms would use positrons. Its nuclear reactions would involve antimatter nuclei. According to the symmetries tested in particle physics, such a star should produce light through processes corresponding closely to those inside an ordinary star. Photons are not labelled with a convenient message explaining whether they came from matter or antimatter. A telescope receiving visible light from an isolated antistar might therefore find it difficult to identify the difference directly. The trouble begins where matter and antimatter meet. If an antimatter star were surrounded by ordinary interstellar gas, the incoming matter would eventually encounter antimatter near the star, and annihilation would occur. Those interactions would produce energetic particles and radiation with characteristic signatures. If entire antimatter galaxies existed beside ordinary matter galaxies, the boundaries between the two regions should be particularly active. Gas from one side would mix with gas from the other, giving protons and antiprotons many opportunities to meet. Astronomers do not see the level of widespread annihilation radiation that would be expected from a universe divided into nearby large regions of matter and antimatter. This does not prove that no isolated antistar exists anywhere, or that every object in the observable universe is definitely matter. It does tell us that large antimatter domains cannot simply be mixed throughout our cosmic neighbourhood without leaving obvious traces. Antiprotons themselves do appear naturally, and their presence is not surprising. The universe contains many high-energy particles known as cosmic rays. Despite the name, most cosmic rays are not rays of light. They are particles, including large numbers of protons and atomic nuclei, travelling through space at high energies. When these particles collide with gas between stars, their energy can create new particle and antiparticle pairs. Among the products can be antiprotons. This gives us a perfectly ordinary source of cosmic antimatter. An antiproton detected in space does not necessarily mean that somewhere nearby there is an antimatter planet, an antistar or an antimatter civilization that has accidentally dropped something. High-energy collisions can make individual antiprotons through the same basic physics used in particle accelerators on Earth. After being created, an antiproton can travel through the galaxy for a long time before encountering matter. Space is extremely thin compared with the inside of a laboratory target or even the atmosphere. The antiproton is still surrounded by a universe dominated by matter, but the distances between particles can be enormous. Magnetic fields in the galaxy can bend the path of the charged antiproton, causing it to wander through space before it eventually reaches a detector or meets something that destroys it. Scientists study these cosmic antiprotons because the number arriving at different energies contains information about how particles move through the galaxy and about where the antiprotons came from. If the measured population matches what researchers expect from ordinary cosmic ray collisions, there may be no need for a more exotic source. If an unexpected excess appeared with a particular energy pattern, scientists would become interested in whether some additional process was producing them. One possibility sometimes discussed involves dark matter. We do not yet know what dark matter is made from, but some hypothetical dark matter, particles could produce ordinary particles and antiparticles when they interact or decay. In certain models, Antiprotons could be among those products. Researchers therefore compare measurements of cosmic antiprotons with predictions from conventional astrophysical sources to see whether anything unusual remains. This is a delicate business, because the ordinary background is difficult to predict perfectly. Cosmic rays travel through complicated magnetic fields. They interact with gas whose distribution is not known with absolute precision. The galaxy is not a laboratory beamline where every target and magnetic field has been placed according to a technical drawing. If scientists see more antiprotons than one model predicts, the explanation might be new physics, or it might simply mean the model of cosmic ray production and transport needs improvement. Nature has a habit of making exciting possibilities compete with slightly less exciting uncertainties. There are also searches for heavier pieces of antimatter. If an antiproton can combine with an antineutron, then in principle antinuclei can exist. Laboratories have produced several kinds of antinuclei in high-energy collisions. Finding heavy antinuclei arriving naturally from space would be especially interesting because their expected production rates in ordinary cosmic ray collisions can be very small. Antihelium is often discussed in this context. A genuine antihelium nucleus contains multiple antiprotons and antineutrons bound together. Producing such a structured object through random secondary collisions is much less likely than producing a single antiproton. If a convincing population of cosmic antihelium nuclei were found, physicists would want to understand the source very carefully. One possibility would be unusual high-energy particle processes. A far more dramatic possibility would be that some large astrophysical object made from antimatter had released antihelium into space. That would be an extraordinary discovery, which is exactly why researchers demand extraordinary care before accepting such a claim. Instruments looking for cosmic antimatter have to distinguish rare antiparticles from enormous numbers of ordinary particles, and a tiny misidentification rate can create misleading events when the background is so large. The situation is therefore slightly ironic. We know that antiprotons exist in space, but detecting them does not solve the matter an antimatter mystery, because ordinary matter processes can produce them. What we really want to know is whether there are signs of primordial antimatter, meaning antimatter that survived from the early universe, rather than being freshly created in later collisions. To understand why that would matter, we have to return to the first moments of cosmic history. The early universe was much hotter and denser than it is today. At sufficiently high temperatures, particles and antiparticles could be created easily from energetic interactions. Matter did not yet exist mainly as calm atoms sitting inside stars and planets. The environment was a dense mixture of radiation and particles repeatedly appearing, interacting, and disappearing. As the universe expanded, it cooled. Heavy particle creation became less frequent because there was no longer enough energy available everywhere to keep making large numbers of particle and antiparticle pairs. Protons and antiprotons that encountered each other could continue annihilating, but eventually new pairs were no longer being produced fast enough to replace them. If there had been exactly one antiproton for every proton and exactly the corresponding balance for the other matter particles, nearly all of the matter and antimatter could have annihilated away. The later universe would have contained abundant radiation but very little of the material required to form the structures we see today. That clearly did not happen. Something left ordinary matter ahead. The imbalance was probably extremely small in percentage terms. For every enormous number of matter and antimatter particles, there may have been only a tiny excess of matter. But when almost all the matching pairs annihilated, that tiny excess became everything that remained. Once the antimatter partners were gone, the leftover protons and other matter particles had nobody left to annihilate with. Over time, those survivors participated in the formation of atomic nuclei. Electrons combined with nuclei to form atoms. Gravity gathered gas into stars and galaxies. Stars created heavier chemical elements. Exploding stars spread those elements into space. New stars and planets formed from the enriched material. chemistry became increasingly complex, and eventually some of that leftover matter organised itself into people capable of asking why the universe had failed to cancel them out. This problem is known as the matter-antimatter asymmetry. It is one of the major unresolved questions linking particle physics with cosmology. We know that the modern observable universe contains much more matter than antimatter. We know of processes in particle physics that can treat matter and antimatter slightly differently. What remains uncertain is whether the known differences are sufficient to produce the enormous cosmic imbalance we observe. Physicists have identified several conditions that a successful explanation would need to satisfy. There must be processes capable of changing the balance of matter-like quantities under the appropriate early universe conditions. There must be some difference between how matter and antimatter behave. The universe must also have experienced periods when it was not sitting quietly in complete thermal equilibrium, because a perfectly balanced equilibrium tends to erase the sort of lasting preference we need. These requirements tell researchers roughly what sort of physics could create the imbalance, but they do not yet give us one experimentally confirmed history of exactly how it happened. Different theories propose different mechanisms. Some place the crucial events at extremely high energies shortly after the beginning of the universe. Others connect the imbalance to properties of particles such as neutrinos. Some suggest additional particles or interactions that have not yet been discovered. The antiproton becomes important here because it offers an extremely clean test of the symmetry between matter and antimatter in a familiar particle. If the proton and antiproton differed even slightly in mass or in the magnitude of their charges, that would immediately reveal that our current understanding was missing something profound. Decades of increasingly precise measurements have not found such a difference. That does not mean the mystery has gone away. It means the easy answers are being removed. Imagine entering a room and discovering that nearly every coin has landed heads up. You might first suspect that the coins are weighted. So you take one coin, test it carefully, and discover that its two sides appear almost perfectly balanced. You test another. The same result. Eventually, the strange arrangement of the room becomes even more interesting because the individual objects refuse to reveal the bias you expected. The proton and antiproton are a little like that. Their measured properties are matched with extraordinary accuracy, yet the universe seems to have selected overwhelmingly one side of the pair. There is also the possibility that antimatter was not destroyed everywhere but was separated from matter during the early universe. Perhaps, one might imagine, matter collected in some enormous regions and antimatter in others. If the regions were sufficiently separated, both might survive without constant annihilation. This idea has been studied in various forms, but it faces serious observational difficulties. Matter and antimatter domains could not simply touch without producing energetic radiation along their boundaries. On very large scales, cosmological observations also place restrictions on how such a separated universe could have developed. The absence of obvious annihilation boundaries across the observable cosmos strongly suggests that our entire observable region is dominated by matter rather than being one patch in a nearby checkerboard of matter and antimatter. It remains possible in principle to speculate about antimatter existing beyond the portion of the universe we can observe, but that is difficult to test. The observable universe is limited by how far light has been able to travel to us since the early stages of cosmic history. Regions beyond that horizon may exist, but if no information from them can reach us, they cannot currently explain a measurement in our laboratories. Science becomes more useful when it stays close to what can actually be tested. Within the observable universe, the evidence points strongly toward matter domination. Black holes sometimes enter discussions of antimatter because they provide extremely energetic environments. A black hole itself is not made of matter in the ordinary sense of having a visible surface composed of protons. Nor is an antimatter black hole a separate known category with opposite gravitational behaviour. If matter or antimatter falls into a black hole, the external gravitational description depends on properties such as the total mass, electric charge, and rotation, rather than on whether the original material was built from particles or antiparticles. The surroundings of black holes, however, can produce antimatter. Gas falling toward a black hole may become extremely hot. Powerful magnetic fields and particle acceleration processes can generate energetic photons and particle collisions. Positrons and other antiparticles can emerge from these environments, and under suitable conditions, antiprotons can also be created. Neutron stars and supernova remnants provide other examples of astrophysical environments capable of accelerating particles to enormous energies. The universe has no shortage of natural accelerators. Some are far more powerful than anything humans can build, although they are less considerate about placing detectors where we want them. What these environments usually produce is secondary antimatter. The antiproton is born during an energetic interaction and may travel away before being detected. This is fundamentally different from discovering an object made from antimatter that has survived since the early universe. The distinction matters because secondary antiprotons tell us that particle physics works in space much as it does in terrestrial experiments. Primordial antimatter would tell us something new about cosmic history. Astronomers therefore search for several kinds of evidence at once. They measure cosmic antiprotons, they look for possible antinuclei, they examine high-energy radiation for signs of widespread annihilation. They study the cosmic microwave background and the distribution of matter on large scales to test models of the early universe. No single observation answers the whole question. There is another interesting clue in ordinary photons. When a proton and antiproton annihilate, they often produce pions and other particles whose decay eventually creates energetic gamma rays. Large-scale matter and antimatter boundaries would therefore contribute a characteristic high-energy glow. The relative quietness of the sky in the relevant ways places strong limits on how much nearby bulk antimatter can be hidden. An isolated antistar remains harder to rule out. If it lived in a region with very little surrounding ordinary matter, the amount of annihilation on its surface could be small enough to make identification difficult. Researchers have considered whether some unusual gamma-ray sources might be consistent with antistars, but no antistar has been confirmed. Even if one were found, it would create another question. Did the antistar form from a surviving pocket of primordial antimatter? Or was there some exotic later process capable of assembling a large amount of antimatter? Either possibility would have enormous consequences for cosmology. At the moment, the simpler picture remains that individual antiparticles are continually produced in energetic events, while large stable structures in our observable region are overwhelmingly ordinary matter. That gives the antiproton a strange status in the universe. It is not forbidden, and it is not even extraordinarily difficult for nature to produce one when enough collision energy is available. Yet it almost always appears as a temporary minority particle in a universe filled with potential annihilation partners. A cosmic ray collision can create an antiproton, which may then spend millions of years wandering through interstellar space. Magnetic fields bend its path. It crosses vast distances between sparse gas atoms. Eventually it may enter the solar system, where the magnetic field carried by the solar wind influences its journey. A detector on a spacecraft might record it, allowing researchers to infer its charge, energy, and identity. For that antiproton, the galaxy has been an enormous trap of sorts, although a very loose and chaotic one. There are no carefully machined electrodes and no cryogenic vacuum chamber. There is simply enough empty space for the particle to survive between encounters. This is one reason cosmic antimatter is so useful. It links the smallest scales of particle physics with some of the largest structures in astronomy. To understand how many antiprotons should arrive near Earth, scientists need to know how particles are created in collisions, how they scatter, how magnetic fields guide them, where gas is distributed through the galaxy, and how energetic sources inject cosmic rays into space. A measurement of one tiny antiparticle can therefore carry information about a region thousands of light-years across. And still the original question remains. Where are all the antiprotons that might once have matched the protons now filling the universe? The most likely answer is not that they are hiding somewhere nearby. Most appear to have been annihilated very early in cosmic history. The antiprotons we detect today are mainly new ones, produced long after that early disappearance through energetic collisions and other high-energy processes. In that sense, a cosmic antiproton is probably not an ancient survivor from the beginning of time. It is more like a recent reconstruction of something the universe once contained in enormous abundance. That idea makes laboratory production seem a little less artificial. When physicists create antiprotons in an accelerator, they are not inventing a substance nature rarely knows how to make. They are reproducing a type of process that has occurred throughout the universe, wherever sufficient energy becomes concentrated. What remains beyond our current understanding is not the existence of antimatter, but its history. Why did the early universe finish with a surplus of matter? Why was the imbalance the size it was? Did known particle processes create it, or is some new physics involved? Are neutrinos part of the answer? Did an undiscovered particle decay differently into matter and antimatter? Was the asymmetry established almost immediately after the beginning of cosmic expansion, or did it develop during a later transition in the young universe? Those questions are difficult because the events happened under conditions we cannot reproduce completely. Particle accelerators can recreate tiny pieces of high-energy physics, but they cannot rebuild the early universe. Cosmological observations show us the outcome, while laboratory experiments test the possible mechanisms. The antiproton sits between those two approaches. In the laboratory, it tells us how precisely antimatter mirrors matter. In cosmic rays, it tells us how antimatter is produced and transported through the galaxy. In cosmology, its absence in bulk becomes part of the evidence that something happened to the matter-antimatter balance long before stars existed. What makes the situation especially interesting is that the mystery does not come from antiprotons behaving badly. It comes from them behaving almost exactly as expected. Nature gives us a proton and an antiproton with matching mass, opposite charge, corresponding internal structure, and closely mirrored physical behaviour. Then, nature builds a visible universe almost entirely from the first one. That is a much more difficult puzzle than simply discovering that antimatter follows different rules. If antiprotons had obviously decayed faster, responded differently to gravity, or possessed a slightly different mass, physicists would immediately have clues to work with. Instead, every increasingly precise measurement seems to remove another straightforward explanation. The question therefore shifts from what is wrong with antimatter to what happened in the history of the universe. And that brings us close to the deepest reason antiprotons are studied at all. They are not merely unusual particles that happen to annihilate dramatically when they meet protons. They are tests of whether the laws governing matter and antimatter are truly as symmetrical as they appear. Every comparison asks whether there is a tiny difference hiding beyond our current precision. Every cosmic ray measurement asks whether some unknown process is producing more antimatter than expected. Every search for antinuclei asks whether somewhere in the universe a much larger population of antimatter has survived. So far, the proton's antimatter twin continues to look remarkably faithful to the original. That leaves us with a final problem more fundamental than how antiprotons are created, trapped, or detected. If the mirror is this good, what exactly is the mirror telling us about the laws beneath both particles, and why does reality seem to have chosen one side of it so completely? By the time we've followed the antiproton from its theoretical beginnings to the inside of particle accelerators, from violent collisions to delicate electromagnetic traps, and from laboratories on Earth to the cosmic rays moving through the galaxy, the particle begins to seem less like an exotic curiosity and more like a question nature has placed directly in front of us. The antiproton is not difficult to understand because it behaves chaotically. It is difficult to understand because it behaves so well. Again and again, experiments show us a particle that resembles the proton with extraordinary precision. It has the same mass. It carries an electric charge of the same size but opposite sign. Its internal structure is built from antiquarks in the corresponding arrangement. Its magnetic behavior mirrors that of the proton in the way our best theories expect. Wherever scientists look for an obvious flaw in the symmetry, the antiproton quietly refuses to provide one. That makes it one of the most useful particles in fundamental physics. If the proton and antiproton were obviously different, the mystery of matter and antimatter might be easier. We could point to the difference and begin asking how that difference affected the early universe. Instead, we are faced with something more subtle. The visible universe is filled with matter, while antimatter appears mainly in small amounts produced by energetic processes. Yet the individual particles seem remarkably balanced. The laws appear to offer us two matching possibilities, while cosmic history seems to have chosen one of them almost completely. To understand why physicists find this so important, it helps to think about what a physical theory is really trying to do. A theory is not simply a collection of descriptions for things we already know. It tells us which relationships should remain true, even when we test nature under new conditions. If the theory says that a proton and antiproton must have equal masses, then measuring those masses becomes more than an exercise in precision. It becomes a challenge to the structure of the theory itself. Suppose the measurements eventually revealed that the antiproton was very slightly heavier than the proton. The difference might be so small that no ordinary machine would notice it. It could be hidden far beyond anything relevant to chemistry, engineering, or daily life. Yet in fundamental physics, such a result would be enormous. It would mean that one of the deepest expected relationships between matter and antimatter had failed. The same is true of electric charge. The proton carries positive charge and the antiproton negative charge. Their magnitudes should match. If the antiproton's charge were even slightly different in size, scientists would have to reconsider some of the assumptions built into modern particle theory. Precision therefore matters because tiny differences can reveal large problems. So far, no such mismatch has appeared. This leaves physicists in the unusual position of becoming more impressed by the symmetry, while becoming less satisfied with the history of the universe. The better the proton and antiproton match, the harder it becomes to explain why one is common and the other is not. There is a deeper principle behind many of these comparisons. Modern particle physics contains a symmetry connecting particles and antiparticles with transformations involving charge, spatial reflection, and the direction of time. The technical details can become complicated quickly, but the central idea is manageable. If nature follows this symmetry exactly, then a system made from matter should have a corresponding antimatter description under the appropriate transformation. This does not mean that every process looks identical if you simply replace a particle with its antiparticle. Some details also involve directions, spins, and the ordering of events. But when all the relevant transformations are considered together, the underlying laws are expected to preserve a particular relationship. The proton and antiproton provide an exceptionally clean testing ground for that expectation, because both can be isolated and measured with extraordinary precision. Researchers can compare their charge-related behavior, magnetic properties, and motion in carefully controlled fields. Every successful comparison strengthens the evidence that this deep symmetry continues to hold. That may sound like scientists repeatedly asking the same question and receiving the same answer. In a sense, they are. But the precision keeps improving. Each experiment asks whether the agreement continues one level deeper. There is a useful difference between knowing that two things look similar and knowing that any difference between them must be smaller than a certain amount. Imagine standing at a distance and deciding that two pieces of paper appear to be the same length. Then you measure them with a ruler and still find no difference. A more precise instrument also finds none. Eventually you are testing dimensions so fine that your eyes could never have noticed them. With each improvement, the statement that the papers are equal becomes stronger. Antiproton experiments work in the same general spirit, although the measurements are far more demanding and the consequences are rather more interesting than stationary. One reason this matters is that the Standard Model, our most successful framework for describing known elementary particles and their interactions, is extremely effective but clearly not the complete description of reality. It does not explain everything we observe. It does not tell us what dark matter is. It does not provide a complete quantum description of gravity. It does not fully explain why the universe contains so much more matter than antimatter. There are also properties of particles whose values have to be determined experimentally, rather than emerging from some deeper explanation we already understand. Physicists therefore know that something lies beyond the present framework, even if they do not yet know exactly what form that something takes. The antiproton offers one place to search. A small disagreement between matter and antimatter could become evidence of physics that the Standard Model does not contain. That is why a measurement confirming another decimal place is valuable even when the result agrees with expectations. Every agreement rules out possibilities. Every failed theory leaves fewer places for new physics to hide. This process can feel frustrating because the universe is not obligated to reveal its deepest secrets quickly. Physicists can spend years improving an experiment only to discover that nature continues behaving exactly as expected. Yet that result still changes our knowledge. A theory predicting a measurable difference is no longer viable if the improved experiment sees nothing. In that sense, the antiproton is both cooperative and stubborn. It allows scientists to trap it, measure it, cool it, transport it, and compare it with the proton, but it does not easily surrender a surprise. Gravity provides another example of how antimatter forces us to separate expectation from assumption. For a long time, popular discussions sometimes imagined that antimatter might fall upward. The idea has a certain intuitive appeal if we mistakenly think anti should mean opposite in every possible sense. If electric charge reverses, perhaps gravity should reverse too, but antimatter does not have negative mass. An antiproton has the same positive mass as a proton. The expectation from established physics is therefore that antimatter should respond to gravity in the ordinary direction. Testing this directly with a charged antiproton is difficult because electric and magnetic forces overwhelm gravity at the scale of a single particle. Even an extremely weak unwanted electric field can have a larger effect on an antiproton than Earth's gravitational pull. This is one reason researchers create antihydrogen. By combining an antiproton with a positron, they produce a neutral antiatom. Because the positive and negative electric charges balance overall, the influence of unwanted electric fields becomes much easier to control. Measurements of antihydrogen have supported the ordinary picture that antimatter falls downward under Earth's gravity rather than upward. Researchers continue improving the precision of these experiments, but the simple fantasy of anti-gravity antimatter has not appeared. Once again, antimatter behaves less dramatically than fiction, and more interestingly for physics. The same pattern appears when antimatter interacts with light. Hydrogen has been studied with astonishing accuracy. Its internal energy structure produces very specific frequencies of absorbed and emitted light. If antihydrogen truly mirrors hydrogen, according to the expected symmetries, the corresponding spectral behavior should match. Scientists can therefore use lasers to test antihydrogen and compare the results with ordinary hydrogen. Any unexplained difference would be extraordinary because the hydrogen system is understood so well. So far, the mirror continues to look remarkably clean. At this point, we might reasonably ask whether the word antimatter makes the whole subject sound more mysterious than it really is. If antimatter obeys the same fundamental framework, has positive mass, falls downward, forms atoms, and behaves so much like matter, perhaps we should simply think of it as another type of matter. There is some truth in that. The distinction is not between normal reality and some opposite reality. Antimatter is part of normal reality. Positrons are used in medical imaging. Antiprotons can be made in accelerators. Antihydrogen can be trapped. Cosmic rays naturally contain antiparticles. Nothing supernatural is required. Yet the distinction remains physically important because matter and antimatter annihilate when the corresponding particles meet, and because the universe contains a striking imbalance between them. The difference is therefore not that antimatter belongs outside the laws of nature. The difference is that the universe seems to have selected an overwhelmingly matter-dominated state, even though the laws allow both. This leads to a question that sounds almost embarrassingly simple. Why is there something rather than almost nothing? Usually that question belongs to philosophy, but antimatter gives it a very specific physical version. If the early universe created equal amounts of matter and antimatter, and if every proton eventually found an antiproton, then most of the material required for stars and planets could have annihilated away. Radiation would remain, but the familiar structures built from ordinary matter would be drastically reduced. The fact that you are here means the cancellation was incomplete. A tiny excess survived. That leftover matter eventually became everything from galaxies to oxygen atoms, to the neurons currently trying to stay awake through a discussion of particle physics. The strange part is that the amount of surviving matter is small compared with what may have existed before the great period of annihilation. The universe did not need to favour matter by an enormous amount. A slight imbalance was enough. Once nearly all matching particle and antiparticle pairs had annihilated, the small surplus became the entire remaining supply. This is why physicists search so carefully for differences between matter and antimatter. A tiny preference in the early universe could have had enormous consequences later. We already know that some particle processes distinguish matter from antimatter in subtle ways. Certain unstable particles and antiparticles do not decay with exactly identical probabilities under all circumstances. These effects are real and important. They prove that nature is capable of introducing small asymmetries between matter and antimatter. The problem is that the known effects do not seem sufficient on their own to explain the observed cosmic abundance of matter. Something else appears to be required. Perhaps additional matter, antimatter, differences exist in particles we have not studied well enough. Perhaps neutrinos play an important role. Perhaps unknown heavy particles existed in the early universe and decayed in a way that slightly favoured matter. Perhaps a phase transition in the young universe created conditions where an asymmetry could develop. There are many possibilities, and the antiproton helps by ruling out some of the simpler ones. If protons and antiprotons had different masses, that might provide a straightforward source of imbalance. Experiments say they do not, at least within extremely tight limits. If their charge magnitudes differed noticeably, that could create another asymmetry. Again, measurements have found remarkable agreement. If antimatter responded to gravity in a completely opposite way, cosmic evolution could have separated matter and antimatter very differently. Present experiments do not support that picture. The antiproton keeps closing doors. That does not make it unhelpful. Science often progresses by discovering which explanations cannot be correct. There is also something important about the antiproton's internal complexity. A proton is not elementary. It contains quarks and gluons, with much of its mass emerging from the energy of the strong interaction, rather than simply from adding the masses of its quarks. The antiproton reproduces this entire complicated system using antiquarks. This means the equality between proton and antiproton masses is more impressive than matching two simple building blocks. The strong interaction inside each particle involves a constantly changing quantum environment. Quarks move, gluons carry energy. Additional temporary quark and antiquark pairs contribute to the internal structure. Despite all of that complexity, the final matter and antimatter particles match. The mirror works not only for the outside label, but through the collective behaviour of the entire system. This tells us something important about the laws underlying matter. They are not casually biased toward the particles from which we happen to be made. A proton may feel more ordinary to us, but the equations do not appear to treat it as more legitimate than an antiproton. If you could imagine an isolated region containing only antimatter, An antiproton there would not know it was exotic. It could become part of antihydrogen. Antiatoms could interact electromagnetically. More complicated antimatter nuclei could exist. Nothing inside that isolated region would require the label strange. We call our side matter because it is the side we live in. From the point of view of an imaginary observer made entirely from antimatter, their antiprotons would be the familiar particles, while a proton from our world would be the unusual object that annihilates when it touches things. This symmetry is easy to describe but difficult to absorb because our experience is so strongly one-sided. We have never had to worry about whether a chair might be an anti-chair before sitting down. Every ordinary object we handle belongs to the same matter-dominated environment. The universe has already made the choice for us. What antiprotons reveal is that the choice may not be built into the simplest properties of the particles themselves. That shifts attention toward cosmic history. Perhaps the universe did not begin with a permanent preference for matter encoded directly into the mass of the proton. Perhaps the preference emerged during a particular period when conditions allowed tiny asymmetries to accumulate. This distinction is crucial. There is a difference between saying nature's basic ingredients are unequal and saying a nearly symmetrical set of ingredients pass through an asymmetric process. Consider a perfectly balanced set of ingredients entering a machine. If the machine treats one side slightly differently for a brief period, the final output can become strongly unbalanced, even though the ingredients themselves were matched. Something loosely similar may have happened in the early universe. The antiproton lets us test the ingredients. Cosmology asks us to reconstruct the machine. These two areas of physics therefore meet around the same mystery. Particle experiments examine matter and antimatter under controlled conditions. Cosmological observations tell us what survived after billions of years of cosmic evolution. Neither approach alone gives the complete answer. There is another reason antiprotons matter beyond the question of cosmic imbalance. They remind us that reality contains possibilities that are almost entirely absent from everyday experience. For thousands of years, humans studied matter without knowing antimatter existed. We learned to build structures, melt metals, classify elements, develop chemistry, and understand electricity using only the material naturally available around us. Then 20th century physics discovered that the familiar catalogue was incomplete. The electron had a positron, the proton had an antiproton, quarks had antiquarks, whole antiatoms could be constructed. It was as though nature had provided us with a book and allowed us to read only every other page until the mathematics hinted that something was missing. This does not mean antimatter is hidden in another dimension or separated from us by some invisible wall. Individual antiparticles are created around us in energetic processes. Positrons can emerge from certain radioactive decays. Cosmic ray collisions produce antiparticles in the atmosphere. Particle accelerators manufacture them deliberately. The antimatter world is not elsewhere. It is another possibility within the same world. That may be one of the most important lessons of the antiproton. What appears rare in our environment does not have to be unnatural. The antiproton follows the same underlying framework as the proton. It can move through empty space. It can be accelerated. It can be trapped. It can interact through the strong force. It can become part of an anti-atom. It responds to gravity. Its rarity tells us something about the history of the universe, not about whether the particle belongs here. And perhaps this is why the antiproton feels like such a perfect shadow. A shadow resembles the object that creates it, but reveals something different about the surroundings. The antiproton mirrors the proton, and that mirror forces us to notice the imbalance surrounding both of them. We begin with an apparently simple comparison. Positive charge on one side, negative charge on the other. Then the comparison reaches deeper. Quarks become antiquarks. Magnetic behavior reverses appropriately. Mass remains equal. Strong interactions build both structures. Antihydrogen mirrors hydrogen. Laboratory measurements keep confirming the relationship. Eventually, the question is no longer what makes an antiproton unusual. The question becomes why protons are so common. every atom around you becomes part of that mystery. The hydrogen in a glass of water contains protons that survived because the early universe somehow had more matter than antimatter. The carbon in your body exists because those surviving particles eventually became stars, heavier elements, planets, and chemistry. The antiproton shows us the alternative that nature could also have used. It is not a fictional opposite and not an incomplete version of matter. It is a genuine partner built into the same physical framework. That is why physicists continue to improve antiproton experiments even after decades of agreement. The possible reward from finding the smallest discrepancy is enormous. A tiny difference could point toward a deeper theory, help explain the matter-dominated universe, or expose a connection between particle physics and cosmology that we have not yet understood. And if no difference appears, that is important too. It tells us that the answer must lie somewhere else. Perhaps future experiments will compare proton and antiproton properties with still greater precision. Perhaps transported antimatter will allow measurements in quieter laboratories. Perhaps antihydrogen experiments will improve gravitational tests. Perhaps cosmic ray detectors will identify an unexpected population of antinuclei. Perhaps neutrino experiments or new particle colliders will reveal the mechanism that gave matter its early advantage. For now, the antiproton continues to do what it has done since its discovery. It gives us a remarkably clean reflection of ordinary matter and then leaves us to explain why the universe hardly contains the reflection. If you look around the room, almost everything you see is evidence of that unanswered question. The walls, the air, your hands, the device playing this video, and the planet carrying all of it through space are collections of particles from the same surviving side of an ancient imbalance. Somewhere in a laboratory, perhaps only a handful of antiprotons are moving quietly inside an electromagnetic trap, prevented from touching the matter surrounding them. They have the same mass as the protons in that equipment, opposite charge, corresponding internal structure, and no obvious sign that nature considers them less fundamental. They are rare here because history made them rare. Understanding exactly how that happened remains one of the unfinished tasks of modern physics, and the proton's antimatter twin continues to offer one of the clearest ways of asking the question,